Hello, and welcome to Sleep Gravity. For the time ahead, you can gently set aside whatever remains unfinished from today and allow your mind to follow a slower journey. We will leave behind the familiar rhythms of Earth and travel into distant regions of space, where the light of a star once flared for the final time before slowly fading into darkness. At first, these may seem like places where every story has already come to an end, but in the universe, an ending rarely brings complete stillness. The light may have weakened, and the old form may have broken apart, yet the matter remains, gravity remains, and motions that began long before the explosion continue along new paths. Perhaps the closest way to imagine this is to think of the moment after a loud sound has just stopped. The room suddenly becomes quiet, but that silence does not mean every vibration has vanished at once. Small tremors continue to travel through the walls and floor, even after our ears can no longer hear them. The air is still shifting, dust is slowly settling, and surfaces continue to hold some of the energy that has just passed through them. Something similar happens after the death of a massive star, except that the scale stretches across many light years, and the echoes can endure for thousands of years. The explosion is over, but the surrounding space is still carrying consequences that have not yet finished unfolding. When a massive star reaches the end of its life, its core may lose the ability to support itself against gravity. The collapse happens with extraordinary speed, triggering an explosion that can hurl most of the star's material outward. For a brief time, the light from this event may become bright enough to stand out among billions of other stars in its galaxy. Then the brightness gradually fades, leaving behind an immense cloud of gas and dust that continues expanding into space. Astronomers call this remaining structure a supernova remnant. It is not the explosion itself, but the long-lasting aftermath that continues far beyond the most violent moment. Through telescopes, some remnants appear as thin arcs, winding ribbons of light, or uneven shells suspended in the darkness. Some look almost like soft clouds, even though the matter within them may be so hot that no familiar environment on Earth could survive there. The colors in astronomical images help us distinguish regions of gas, different energy levels, or different elements, sometimes giving a remnant such a quiet beauty that it is difficult to connect it with the. It is from this contrast that the image of a stellar graveyard emerges. A place that preserves the traces of stars that have lost their former structure, regions of space where familiar light once existed and where only fading layers of matter now remain. And yet, a stellar graveyard does not lie still. Its outer shell continues to expand, carrying atoms that once rested deep inside the star. Shockwaves still move through the thin gas between the stars, traveling more quickly through sparse regions, then slowing down and glowing more brightly when they encounter a denser cloud. Different parts of the same remnant do not cool at the same rate, nor do they hold their shape like statues frozen in space. If we could watch the entire process accelerated thousands of times, the cloud that seems motionless would appear almost like a structure breathing very slowly, expanding, colliding, bending, and gradually blending into the galaxy around it. These changes are difficult to notice not because they are absent, but because a human life is so short compared with the rhythm of a remnant. A photograph taken today and another taken several months later may look almost identical, but when astronomers compare observations separated by many years, subtle differences begin to emerge. An edge has shifted, a knot of gas has grown brighter, part of the shell has faded, as the material has spread more thinly. The universe does not freeze after the explosion. It simply moves into a rhythm so slow that recognizing it requires the patience of generations of observers. Even then, the expanding cloud is not the whole story. Hidden behind those layers of matter may be the surviving core of the original star, compressed into an object far smaller than before, yet still capable of profoundly affecting the space around it. Some remnants contain a rapidly spinning neutron star. In other cases, the collapse may leave behind a black hole that is nearly impossible to observe directly. In still other systems, A star that once orbited the star that exploded may remain, continuing its motion through the material left behind by the blast. These possibilities do not need to be fully opened just yet, but their presence alone reveals that the center of a remnant may be far more complex than its quiet appearance suggests. The secret life within these stellar graveyards, then, is not biological life as we know it on Earth. It does not refer to creatures hidden beneath cosmic dust, but to another kind of continuation, motion that has not stopped, heat that has not fully dispersed, gravity still rearranging matter, and surviving celestial objects, continuing to influence one another. A star is dead in the sense that it no longer maintains its former shape or source of energy. But that does not mean all the matter that once formed, it suddenly becomes meaningless or motionless. What remains may continue to glow at wavelengths invisible to the human eye, produce streams of high-energy particles, or quietly change in brightness over many years. What makes this especially remarkable is that much of this activity remains completely hidden if we observe only visible light. Human eyes can detect only a very small portion of the full spectrum of light in the universe. A remnant may appear faint in familiar wavelengths, yet become clearly visible in radio waves, infrared light, or X-rays. Each kind of telescope is like a different sense, allowing us to recognize a layer of reality that was previously beyond our view. Hot regions of gas, compressed magnetic fields, and small sources of energy buried deep within the remnant may appear only when we learn to see the universe through many different forms of light. At times, long-term observations reveal something even stranger. Some points of light within a remnant do not merely persist, but change. They brighten, fade, or vary more dramatically than expected from a cloud of gas that is simply cooling over time. Each change is like a faint signal emerging from within the cloud, suggesting that a separate process may still be taking place there. Something may still be spinning, still drawing in matter, still colliding, or still releasing energy. The moment of the explosion has receded into the past, but the physical story of the system did not end with it. From our distant perspective, all of this unfolds in silence. No sound of the explosion travels through the vacuum. There is no audible collision between layers of gas, and no change happens quickly enough for the unaided eye to notice in a single night. There is only light leaving the remnant, crossing immense distances, and finally reaching telescopes waiting around Earth. Within that light is information about temperature, velocity, chemical composition, and movements that began long ago. By reading these subtle signs, we gradually come to understand that a stellar graveyard is not a sealed chamber containing the past, but a region of transition where matter is learning to exist in different forms. The original star will never return. The layers of gas that once formed its surface have been driven away, its old structure has broken apart, and the balance that kept it stable for millions of years is gone. But the explosion cannot erase matter from the universe. It can only scatter it, compress it, or send it into new orbits. The core may become an entirely different kind of object. The outer gas continues to meet the surrounding environment of the galaxy. Elements that once lay deep inside the star begin a long journey that may last far longer than the life of the star that created them. And so, behind the quiet appearance of a supernova remnant lies a question that will remain with us throughout this journey. When the familiar light of a star has gone out, what continues to move within the darkness? To find the answer, we must return to the time before the explosion, before the layers of gas were torn away from the star, and before its core was compressed into something strange and unfamiliar. The star was still whole then, still shining, and still held in a balance that seemed remarkably enduring. Gravity was constantly pulling everything inward, while energy rising from deep within the core resisted that collapse. For millions of years, these two forces quietly held each other in place, creating a star that appeared stable in space. Yet even within that long-lasting balance, its limits had been present from the beginning, and the star's ending was being prepared in a way slower than anything a human being could observe within a single lifetime. Long before it became a thin cloud spreading through space, that star had once been an almost perfect structure, held together by its own internal balance. From the outside, it appeared only as a steady point of light, revealing nothing of the streams of energy moving through each layer of matter, or of the immense weight the core had to quietly resist. Light continually left its surface with such regularity that a distant observer might imagine the star would remain that way forever. But this stability was never true stillness. It was more like a motionless rhythm created by countless movements, a lasting state made possible only because opposing forces continued to hold one another in just the right way, at just the right strength, from moment to moment. Before that light and balance existed, the matter that would form the star had been scattered through a cold region of gas within the galaxy. It was not a cloud with clear edges like those above Earth, but a vast expanse of space containing mostly hydrogen and helium, along with a small amount of heavier elements left behind by earlier generations of stars. If we could travel through such a region, we might not feel that we had entered anything unusual, because the particles would be separated by enormous distances, and darkness would still fill almost all of the space around us. Yet even within that emptiness, gravity was never entirely absent. Every particle pulled on every other particle, faintly but without pause, and over a long enough span of time, those tiny attractions could begin to transform an entire region. One part of the cloud gradually became denser than its surroundings. It may have been compressed by the motion of gas within the galaxy, by the influence of nearby stars, or by a shock wave from an explosion that had occurred earlier. The exact cause could vary, but once enough matter began gathering in the same place, the contraction started to strengthen itself. Greater mass created stronger gravity, and stronger gravity drew in even more gas and dust. From a faint region within the cloud, a center of attraction began to form, silently pulling surrounding matter inward like an invisible current. The deeper the material fell toward the center, the faster it moved. Particles collided, became compressed, and grew hotter, gradually separating the central region from the coldness of the original cloud. At this stage, there was not yet a star in the full sense of the word. The young body of matter glowed mainly because gravity was heating it, as though the inward fall itself were being converted into warmth. Streams of gas continued to circle around it, forming swirling structures and feeding more material into the center. For a long time, the future star existed as something still being built unstable, without a lasting source of energy, but already too massive to return to its earlier state. As the core continued to contract, the temperature rose until processes impossible under ordinary conditions began to become possible. Hydrogen nuclei, which normally repel one another because they carry the same positive charge, moved fast enough to come extremely close together. Under those intense conditions, some of them fused, forming helium and releasing energy. This was the moment when the star no longer shone only because gravity was compressing it. A new source of energy had been ignited deep within the core, one that was more enduring, more powerful, and capable of supporting the star through a large part of its life. We often say that a star is burning, but this burning is nothing like the flames we see on Earth. There is no wood, no oxygen, and no surface of fire flickering in the air. What happens in the core is nuclear fusion, where light atomic nuclei combine to form heavier ones, and a very small portion of their mass is converted into energy. That tiny amount, repeated an unimaginable number of times every second, creates a source of light that can endure for millions or billions of years. A star does not shine because matter is simply being destroyed. It shines because matter is being transformed. The energy created in the core does not escape to the surface immediately. It must pass through dense layers of matter, where it is continually absorbed, re-emitted, scattered, and redirected. A particle of light may take an extremely long time to complete its journey from the central region to the outside. Even though once it leaves the surface, it can cross the vacuum at the greatest speed nature allows. The light we see from a star is therefore the final result of processes that began deep within it long ago. The exterior may appear calm, but inside is a system constantly carrying energy outward from the core, while gravity continues trying to pull the entire mass back toward the center. It is this opposition that creates the balance mentioned at the end of our previous journey. Gravity pulls inward, while the pressure of hot matter and energy within the star pushes outward. Neither side truly stops, and neither completely wins. If the pressure weakens, the star contracts. That contraction heats the core, causing the reactions to intensify and produce more pressure. If energy is generated too rapidly, the outer layers expand, the core becomes less compressed, and the reaction rate may slow. In this way, a star can regulate itself within certain limits, like a system continually restoring its balance whenever it shifts slightly out of place. This balance can last for periods far beyond any scale familiar to a human life. A civilization might appear, develop, and disappear while the star changes almost nothing about its outward appearance. Planets may complete billions of orbits, while the point of light at the center of their system continues releasing energy at a relatively steady rate. Yet beneath that endurance, the fuel in the core is still being consumed. Every moment the star shines is also a moment when its inner composition changes a little more. Old age does not arrive as a sudden event from outside. It is created slowly by the very process that allows the star to continue existing. For massive stars, life unfolds at a much faster pace. They contain more matter, but the weight of that matter makes their cores hotter and more strongly compressed. Nuclear fusion therefore proceeds at a far greater rate, causing the star to shine intensely while consuming its fuel quickly. A massive star may glow thousands of times more brightly than the sun, or even far beyond that, but such brilliance is not a sign of a long life. Instead, it reveals that energy is being released at a rate smaller stars could never sustain. There is a quiet paradox in all of this. Massive stars are born with more fuel, yet their very size causes that fuel to be consumed far more quickly. They live brighter, hotter, and shorter lives, while a smaller star may endure for an immense span of time at a gentle pace of energy release. A high-mass star passes through the stages of its existence relatively quickly on the cosmic scale. It is like a broad, powerful river, carrying more water, yet moving through the landscape with greater speed, never remaining in any one place for very long. As the hydrogen in the core gradually runs low, the star can no longer maintain its original balance. The energy produced at the center begins to decline, while gravity continues pulling inward just as it always has. The core starts to contract, becoming hotter and denser, while the outer layers respond by expanding. The star enters a new form, larger, more complex, and less stable than before. Its surface may become cooler even while its total energy output remains enormous, giving the star a redder color and causing it to swell to a size that is difficult to imagine. The contraction of the core does not simply mark a decline. It also creates the conditions for a new kind of fuel to become active. When the temperature rises high enough, helium can fuse into heavier elements, releasing more energy and temporarily restoring the balance. The star seems to have found another way to continue existing. But this new stage does not last as long as the one before it. Each new fuel requires a higher temperature. Each new layer of reactions operates for a shorter time, and every time the star saves itself from collapse, the period of calm that remains grows smaller. Inside an aging massive star, the structure gradually separates into many layers. Hydrogen may still remain near the outside. Deeper within are regions where helium is undergoing fusion, followed by layers containing carbon, neon, oxygen, and increasingly heavy elements. These are not rigid rings lying motionless like layers of rock, but regions of intensely hot matter, constantly moving, exchanging energy, and changing their composition. They are often compared to the layers of an onion, but inside this cosmic onion, every layer is under tremendous pressure, and each one is sustained by a different chain of reactions. As the star approaches the end of its life, the pace of change grows faster. It may spend millions of years using hydrogen, but heavier fuels do not provide the same amount of time. The later stages shrink from hundreds of thousands of years to thousands, then from years to even shorter intervals. Processes that unfolded gradually through most of the star's life begin to gather closer together, as though an internal clock were accelerating. The surface remains immense and brilliant, but deep within the core, each stable state has become only a brief pause before the next contraction begins. No one can observe the entire life of a star in the way we might watch a tree grow from a seed and eventually decay. Stellar timescales are far too long compared with the whole of human history. Instead, astronomers study countless stars at different stages of life, much like walking through a forest where young trees, mature trees, and ancient trunks all exist at once. Young star clusters reveal newly formed stars. Red supergiants show us the later stages. Explosions and the remnants they leave behind reveal what happens when the final balance is broken. Light also carries signs that the unaided eye cannot recognize. When separated into a spectrum, it reveals which elements are present in the outer layers, how hot the star is, and in which direction it is moving. Its brightness, color, size, and patterns of variation allow scientists to compare observations with physical models of the stellar interior. We cannot open a star and look directly into its core, but we can read changes at its surface much as we might study subtle patterns on water to understand the current flowing beneath. Through this evidence, one truth gradually becomes clear. A massive star does not grow old simply by cooling and fading away. It continually reorganizes its core, shifts to new kinds of fuel, and rebuilds its balance for periods that become shorter and shorter. Each contraction allows it to move further into the creation of heavy elements, but also brings it closer to a limit that fusion can no longer overcome in the same way. That limit appears when the core becomes rich in iron. During the earlier stages, fusing lighter nuclei can release energy, and that energy helps resist gravity. But iron occupies a special position. Continuing to fuse iron nuclei does not provide the useful energy needed to support the core as the earlier reactions did. The star has climbed through many steps of nuclear fusion, but at this stage, the path that once helped delay its collapse has nearly come to an end. The presence of iron does not mean the star explodes immediately. The core continues receiving more material from the surrounding fusion layers, growing heavier and becoming more strongly compressed. For a short time, unusual states of matter still help it withstand the pressure. But the core cannot continue gaining mass forever while keeping the same structure. Gravity has accompanied the star since it was only a cloud of gas, quietly gathering matter, heating the center, and opening the way for fusion. Now, as the useful energy within the core becomes too weak, the same force that helped create the star begins preparing to pull it into an entirely different state. Strangely, the outer regions may offer no clear warning that this limit is approaching. The star is still shining, still releasing heat, and still occupying an enormous volume of space. If a world existed far enough away to observe it, its inhabitants might continue seeing the same familiar point of light, unaware of how fragile the structure deep within the center had become. The most important changes are taking place beneath many thick layers of matter, in a region no eye could ever see directly. This is not the quiet of a system that has stopped working, but the quiet of a balance nearing its limit. The outer layers are still being supported. Energy is still reaching the surface, but the core is finding it increasingly difficult to reach another state that can hold gravity back. Earlier contractions raise the temperature and open the way to a new reaction. This time, that path no longer leads to an energy source capable of preserving the structure for long. For most of its life, the star survived through its ability to adjust. When pressure fell, the core contracted and grew hotter. When the reactions intensified, pressure was restored. But every self-regulating system has a limit, and for a massive star, the final limit lies deep within a core invisible to human eyes. Eventually, contraction is no longer a slow transition into a new state of balance. It becomes a collapse, unfolding far more quickly than the millions of years that brought the star to that moment. Just before that instant, the enormous object may still appear almost completely intact. Light continues leaving its surface, entering space and beginning long journeys across the galaxy. Some of those rays may still be traveling toward Earth even after the star at their source has ceased to exist in its former shape. Distance means that we always see the universe as it was in the past, and so a peaceful point of light in the sky may sometimes be only a delayed image of a state that ended long ago. At the star itself, however, there is no delay created by distance. The core continues bearing the weight of the layers above it. Conditions within move ever closer to the final threshold, where the balance that once supported the entire star can no longer be restored. The change has been prepared over millions of years, but once it truly begins, time will no longer move at the slow pace of stellar aging. And when that balance breaks, a star does not simply disappear. It leaves several traces at once: a moment of brilliant light, a cloud of matter that continues to expand, and perhaps a dense core remaining at the center. These three traces are often viewed as parts of a single story, but each belongs to a different stage and carries its own rhythm of time. To enter the graveyards of stars without becoming lost among layers of light, hot gas, and surviving objects, we must distinguish them clearly. The explosion is not the remnant, the spreading cloud is not the core, and the core is not everything the star leaves behind. When the final balance gives way, one life ends, but at that same moment, three new stories begin to unfold. When the final balance breaks down, the star does not vanish from the universe like a lamp being switched off. Its familiar light may be gone, and the form it maintained for millions of years may be shattered, but that ending does not leave behind a clean, empty space. Instead, it creates three distinct traces, each continuing at its own pace and carrying a different part of the old star's story. The first trace is the brilliant flash of the explosion. The second is the cloud of matter that continues expanding long afterward. The third is the dense core that may remain near the center. These three are closely connected, but they are not different names for the same object. A supernova explosion, a supernova remnant, and a neutron star or black hole are three separate outcomes born from the same transformation. We might imagine them as the first strike of a bell, the sound continuing to travel through the air, and the bell itself remaining after the opening note has faded. The strike is the briefest and most easily recognized event. The echo lasts longer, changing as it moves across different distances, and the bell, though no longer producing that first sound, remains as the source of everything that followed. For a massive star, the first trace appears when the core can no longer resist the weight of the material above it. The collapse happens with extraordinary speed compared with the long life that came before. The star spent millions of years building the layers within it, yet its final balance may break in a span of time almost too brief to imagine. The central region is compressed, while the outer layers are drawn into a violent transformation and eventually driven outward into space. The light from this event can rise dramatically, allowing a single star to stand out for a time among the countless others in its galaxy. From a great distance, observers cannot see each layer of matter shifting and moving. What they first receive is simply a new point of light, appearing in a place that may previously have seemed unremarkable. That point brightens, remains luminous for a while, and then gradually fades as the material expands and the energy spreads outward. Throughout history, people sometimes witnessed such lights without understanding what they truly were. They called them new stars or guest stars because they appeared unexpectedly among the familiar patterns of the sky. Only much later, as astronomy advanced, did we come to understand that these were not newly born stars, but often the final light of stars undergoing the greatest transformation of their lives. That brilliant moment is the supernova. It is an event the instant when the old structure breaks apart and energy is released. Once the brightest light has passed and begins to decline, The supernova no longer exists in the sense of an active outburst, but that does not mean all of its traces disappear. On the contrary, the matter thrown outward has only just begun a journey that will last far longer. This is the second trace, the supernova remnant. If the explosion is a moment, the remnant is the landscape created in its aftermath. It consists of gas, dust, and elements that once belonged to the star and are now expanding into the space between other stars. The outer shock wave continues moving through its surroundings, compressing and heating the matter it encounters. Different parts of the cloud do not travel in exactly the same way, because the explosion does not distribute energy evenly through every layer, and the surrounding environment is not equally dense in every direction. For this reason, a remnant rarely maintains a perfect shape. Some develop into nearly circular shells, while others appear as broken arcs, delicate filaments of gas, or uneven patches of brightness and shadow. One side may expand farther because it is moving into a thinner region of space. Another may slow when it meets a dense cloud of gas, becoming hotter and brighter. The final shape reflects both the explosion itself and the environment through which the remnant is moving. This helps explain why supernova remnants photographed through telescopes often possess such intricate beauty. They are not random clouds suspended motionless in the darkness. Every curve and every bright region is evidence of movement. Filaments of gas reveal where matter has been compressed. Empty spaces show where the cloud has expanded or where the surrounding density is lower. The entire structure is a history still being written through heat, velocity, and gravity. The remnant also survives far longer than the supernova's original brilliance. The outburst may change noticeably over days, months, or years, but the material left behind continues evolving for centuries and millennia. An observer could be born, live an entire lifetime, and pass away while the remnant changed only slightly. Yet when images taken far enough apart are compared, that motion begins to reveal itself. The outer edge has shifted outward, one region of gas has brightened, while another has faded as the material gradually becomes more diffuse. An astronomical image, then, is not a picture of something that has already reached its final state. It is only a single slice preserved from within an ongoing process. Clouds that seem motionless are still expanding. Their light continues to carry information about temperature, composition, and velocity. As we observe them with different kinds of telescopes, different layers of the remnant gradually come into view, though those details will become more important later in our journey. For now, there is only one simple idea to keep in mind. A supernova remnant is not an explosion frozen in space. It is the aftermath still evolving after the brightest light has passed. The cloud continues to move, continues to interact with the galactic environment, and continues carrying the matter of the old star farther from the place where it was born. But not all of the star is scattered into the expanding cloud. In some collapses of massive stars, the central region may remain behind in a different form. This is the third trace, far smaller than the remnant, yet potentially containing the most highly concentrated matter in the entire system. If the core settles into a sufficiently stable state after being compressed, it may become a neutron star. If the collapse continues further, a black hole may form. These two objects are very different, but they share the same meaning. The center of the star does not disappear. It is transformed into a new state, where density and gravity exceed anything familiar in everyday life. Compared with a cloud that may stretch across many light years, the surviving object at the center is almost insignificant in size. A neutron star is only about as wide as a city, while the remnant around it may be trillions of times larger. A black hole is even more difficult to recognize because it has no glowing surface for human eyes to see. Within a vast and luminous cloud, the dense core may remain hidden like a tiny point in an immense painting. Finding it is therefore not always easy. Sometimes the compact object produces signals strong enough to reveal its presence. In other cases, it is concealed by gas and dust or becomes visible only through its influence on the surrounding matter. nor does it necessarily remain at the exact geometric center of the cloud, because asymmetries in the explosion can send the core moving in another direction. Yet, whether it is clearly detected or still hidden from view, the possible presence of a surviving core makes the remnant far more complex. An expanding cloud is not merely matter flying away from the place where the explosion occurred. Within it, there may still be an object spinning, cooling, or shaping its surroundings through gravity and magnetic fields. These processes will unfold later, as we move deeper into the secret sources of light hidden within stellar graveyards. The three traces therefore exist on three different timescales. The supernova is the most dramatic moment of transition, flaring brightly before fading. The remnant is the longer story of matter spreading into space. The compact core may continue to exist for far longer still, even after the outer cloud has gradually blended into the galaxy and become difficult to recognize. When all three are viewed together, the death of a star no longer resembles a single ending. It is more like a separation. Light follows one path, matter follows another, and the core may enter an entirely new state. None of these preserves the star's former shape, yet none of them simply vanishes. Each carries part of the old history forward and continues to influence what happens next. And yet, one important character is still missing from this story. Until now, we have imagined the star as though it lived, aged, and exploded alone. That makes the process easier to understand. But it is not always how stars exist in reality. Many are born alongside another star, moving together within the same gravitational system and shaping one another's lives. If the star that exploded once belonged to a binary system, its three traces do not remain among anonymous gas and dust alone. The explosion may occur beside a star that is still alive. The ejected material may sweep across that star's surface. An orbit that remained stable for millions of years may be disrupted or transformed in a single moment, and if the system stays bound, the surviving star may continue orbiting the newly formed neutron star or black hole. In that case, the stellar graveyard does not preserve only the remains of a lost star. It also contains a witness that is still shining, a star that was close enough to carry the physical memory of the explosion in its own surface and motion. To meet that witness, we must leave behind the image of a solitary star and enter the world of binary systems, where 2 points of light can be born together, orbit one another for millions of years, and eventually reach very different endings. Because before there could be a survivor within a stellar graveyard, there were once 2 stars sharing the same orbit. If the orbit is viewed nearly edge-on, one star may pass in front of the other and block part of its light. The system's total brightness falls, then rises again as the 2 stars move out of alignment. After a certain interval, the dimming repeats with the same rhythm. It is this regularity that reveals how a point of light that seems solitary may actually contain 2 objects moving within a shared orbit. In systems where no eclipse occurs, the spectrum can still reveal what the unaided eye cannot separate. When one star moves toward Earth, the signatures of elements in its light shift slightly in one direction. When it moves away, those same features shift in the opposite direction. If this pattern repeats, the light is telling us that the star is alternately approaching and receding, drawn along its orbit by another object. From these motions, astronomers can estimate the masses of stars. No scale is large enough to place a star upon it, but gravity has already provided a natural way to weigh them. By observing 2 objects pulling each other into motion, we can estimate the mass hidden behind their light. This is one reason binary systems are so important. They allow distant points of light to become objects with measurable masses, orbits, and histories. But their greatest importance to this story lies elsewhere. A binary system explains how a star can still be shining inside the remnant of another star that has already exploded. That survivor did not happen to pass through the cloud later. It was there from the beginning, born within the same region of gas, sharing millions of years of orbital motion and experiencing the effects of every change unfolding within its companion. As the more massive star moved rapidly through its final stages, the other continued orbiting the system's common center. It may have received matter, had its rotation altered, or acquired outer layers different from those it possessed at birth. Yet deep within the larger star, the final reactions were approaching their limit. The two companions continued completing one orbit after another, while the internal clock of one star counted more quickly through its remaining time. From the surface of the companion star, if there were some way to observe the scene, the larger star would likely fill a significant part of the surrounding space. It would not appear as a distant point of light, like the stars seen from Earth, but as a nearby, brilliant celestial body, continuously shaping the system through gravity, radiation, and stellar wind. The distance between them would still be immense by human standards, yet small compared with the scale across which material from a stellar explosion can travel. Until the final moments, the orbit may still appear steady. There is no simple signal announcing that one member is only a short time away from collapse. The massive star continues to shine, its outer layers remain expanded, and the smaller companion keeps moving along the familiar path it has followed through countless revolutions. But within the hidden core, the ability to resist gravity is approaching its final limit. Then the balance that endured for millions of years is broken. The surviving star does not witness the event from a distant and protected place. It lies directly beside the source of the outburst. Light and radiation cross the space between the two stars first, followed by layers of matter hurled outward at tremendous speed. The gravity of the entire system also changes as part of the exploding star's mass is suddenly driven away. In a very short time, the orbital dance that persisted for millions of years is no longer guaranteed. The system may be torn apart, sending its two remaining members away along different paths. But in some cases, the bond does not completely break. The surviving star remains in orbit, no longer moving beside an ordinary star, but around a core that has been transformed into an entirely different kind of object. Before we can know whether that orbit will continue, there is still one moment we must examine closely. What happens when a star explodes directly beside another star? Survival does not simply mean avoiding destruction. The companion must pass through an overwhelming burst of light, a stream of hot material, and a gravitational change powerful enough to rewrite the motion of the entire system. And if it remains afterward, it will not return unchanged. Across its surface, within its velocity, and through its new orbit, the star will carry the traces of the day its companion vanished from its former shape. During its final orbits, the binary system may still retain the same calm appearance it carried for millions of years. The two stars continue moving around their common center, repeating their familiar paths so steadily that nothing at the surface suggests the entire structure is about to be transformed. One member is still shining through a stable source of energy in its core, while the more massive star has moved deep into the final stages of its life. Beneath its immense layers of gas, the core is becoming heavier, denser, and increasingly difficult to support. Yet the most important changes are taking place where light from outside can never reach directly. To the companion star, its neighbor is still the same familiar, brilliant presence, still pulling it along the old orbit and seemingly still sharing the same future. Then the final balance breaks without a long period of warning. The core begins to fall inward upon itself, no longer contracting gradually as it did during earlier adjustments, but collapsing so rapidly that the star's entire long history seems compressed into a single moment. The outer layers have no time to respond to this new rhythm, while the foundation that once supported them from below no longer exists in the same form. A star may spend millions of years forming, shining, and building layers of elements within itself. Yet once the final limit is crossed, its old structure can be destroyed in a span of time almost too brief to imagine. The companion does not observe this event from a distant and protected location, as Earth observes isolated points of light across the galaxy. It remains in the orbit that has held it there since both stars were young, close enough that the collapsing star may fill a large region of the surrounding space. The distance between them, though immense by every human measure, is not enough to separate the surviving companion from what is about to sweep across the system. It cannot suddenly change direction or leave its orbit before the event begins, because the motion of celestial bodies is governed not by choice, but by velocity, mass, and gravitational forces established long ago. The first thing to reach it is light. In an instant, the side facing the explosion is illuminated more intensely than ever before. Not by the steady light the two stars exchange through countless orbits, but by a sudden release of energy as the companion's old structure breaks apart. Along with visible light come high-energy forms of radiation that cross the distance between the two objects, heating and ionizing the outer layers of gas. One side of the star must endure a violent surge of energy, while the other remains turned toward darker space, creating an imbalance that never existed during the system's ordinary state. If we could observe the scene from nearby without being drawn into the event, we would not see a small point of light like the one seen through a telescope. We would see a region of space almost completely filled with matter and radiation. The companion that once held the form of a glowing sphere of gas has now become the source of an immense motion, spreading in every direction. Light moves ahead, crossing the orbit in only a short time, but behind it come heavier and slower layers of matter, capable of leaving much deeper changes upon the surviving star. The outer layers of the collapsing star are hurled into space at tremendous speed. They do not form a smooth, uniform wall, but consist of many regions of gas with different densities, compositions, and velocities, like an expanding sea of matter, in which every current carries its own history. Some material once lay near the surface of the old star. Some comes from deeper layers where heavy elements were formed. Other regions are profoundly altered during the explosion itself. When the sea of matter crosses the distance between the two stars, it reaches the companion not as a gentle wind, but as a stream carrying heat, momentum, and the chemical traces of a star that has just lost its former shape. The surface of a star is not a hard shell with a clearly defined boundary. It is the outermost region of a sphere of plasma, where density gradually decreases with distance and matter is held mainly by gravity. When the gas from the explosion arrives, it does not simply bounce away as an object would after striking stone. Instead, it enters the outer layers, compressing and heating them while carrying motion deeper into the star. The gas farthest from the center, already held more weakly, may be stripped away and absorbed into the expanding debris. What remains is disturbed and distorted, then forced to seek a new state of balance after the impact has passed. The degree of damage depends on many conditions that were determined long before the explosion. If the two stars are separated by a greater distance, the ejected material has more room to spread out, reducing its density before it reaches the survivor. In a tighter orbit, the companion faces a denser and more powerful impact. A star with swollen, loosely bound outer layers will lose material more easily than a compact star whose gravity holds its gas more firmly. Its size, mass, rotation rate, and stage of evolution all help determine whether the explosion strips away only a thin outer layer or causes deeper changes throughout its structure. Even so, the star's existence does not necessarily come to an end. Its core may remain stable, nuclear fusion may continue, and most of its mass may still be held together by its own gravity. In that case, the star survives the explosion not because it escapes untouched, but because its deeper layers are strong enough to preserve the structure after the outer regions have been heated and partially stripped away. Survival here does not mean remaining intact. It means that the star retains enough matter to continue being a star, even though its surface, brightness, and motion are no longer what they once were. In the period after the impact, the outer layers may swell as the newly absorbed heat takes time to escape. The surface becomes larger, cooler in some regions, and brighter at other wavelengths, then gradually contracts as the energy is released into space. The entire star may oscillate like a broad surface of water after a heavy object has fallen into it. though these ripples move through hot plasma and may persist for periods enormous compared with a human lifetime. From far away, the star remains only a point of light, yet changes in that point's brightness and temperature may reveal that it is recovering from a powerful external impact. Some of the material from the explosion is not carried onward, but captured by the survivor's own gravity. Elements that once belonged to the collapsed star may settle into the outer layers, mix with the material already present, and leave behind a chemical trace that is small but significant. The explosion has passed, and the remnant continues to expand, yet light from the surface of the surviving star may still carry a memory of the matter that struck it. When that light is separated into a spectrum, astronomers may find certain elements present in unusual amounts, suggesting that their origin does not lie entirely within the star's own history. Such chemical evidence is rarely clear enough to tell the whole story on its own. The captured material may form only a very thin layer before internal currents mix it deeper into the star or gradually dilute it over time. Other processes can also create similar compositions, so the presence of an unusual element alone is not enough to prove that the star once stood beside a supernova. But when the chemical signature appears alongside a suitable location, an unusual rotation rate, and motion that differs from nearby stars, several pieces of evidence begin to come together into a more reliable history. The star's rotation may also be changed by the impact. Material arriving from one direction does not necessarily pass directly through the center, so it may add rotational motion to the outer layers or strip away matter carrying angular momentum. If the two stars had already exchanged gas before the explosion, the survivor may have been rotating rapidly because it once received material from its companion. The final impact does not create the entire present state, but continues modifying a history that was already complex. What we later measure is therefore the layered result of many stages: the formation of the system, the exchange of matter, the long sequence of orbits, and finally the moment when the explosion swept across the star's surface. A surviving star can carry many traces like these and still appear almost ordinary in an image. There are no visible cracks, no clear boundary showing where the stream of matter once struck, only light carrying subtle changes in temperature, composition, and velocity. Astronomy often has to read enormous stories from deviations this small. Motion that is slightly faster than expected, a spectrum that looks a little unusual, or a rotation rate that does not fit the star's age, may be all that remains of an event that took place hundreds or thousands of years ago. While the survivor struggles to recover its balance, the gravitational system as a whole has also changed in a more profound way. Its former companion was once an enormous sphere of gas, with mass distributed across many vast layers. After the explosion, most of those layers have been driven outward, while the central region may have been compressed into a tiny neutron star or collapsed further into a black hole. In a very short time, the surviving star goes from orbiting a broad, luminous celestial body to moving beside an object incomparably smaller in size, yet extraordinarily concentrated in mass. This transformation does more than make the system look unfamiliar. When a large amount of matter is expelled, the total mass holding the two members in orbit is reduced. Before the explosion, the companion star moved at a velocity balanced by the gravity of the entire system. Immediately afterward, it still carries the same velocity, but the pull that once curved its path is no longer as strong. It continues moving in the direction given to it by the old orbit, even as the gravitational structure around it has changed almost instantaneously. We might imagine an object moving in a circle because a cord holds it along a curved path. If the cord suddenly weakens, the object cannot instantly settle into a new circle. It continues in the direction it was already moving, while being pulled back with less force than before. In a binary system, there is no visible cord, but gravity has played a similar role for millions of years. When the mass decreases rapidly, the old orbit cannot remain unchanged, and the outcome depends on how much material was lost, the velocities of both objects, and the direction in which the newly formed core begins to move. That core does not necessarily remain where it was. The explosion may be uneven, giving the neutron star or black hole a push in a particular direction. Although this change occurs over only a brief interval, it can determine the system's future for millions of years. If the push sends the two objects apart more quickly, their gravitational bond is more likely to break. If its direction happens to keep them close enough or reduces their relative speed, the system may survive, though the new orbit will no longer resemble the one that came before. In systems that are torn apart, the surviving star does not need a continuous force to send it racing through the galaxy. It simply continues with the orbital velocity it possessed at the moment the bond was broken. Before then, gravity had always curved its motion around the common center. Once that pull is no longer strong enough, the star follows a more open path, carrying the speed of its former orbital dance like an invisible trace. Such stars can become runaway stars, moving much faster than many nearby objects, and sometimes allowing astronomers to trace their paths backward toward the region where the explosion occurred. But not every orbital dance comes to an end. In some cases, the amount of mass lost is not enough to free the two members completely, or the newly formed core receives a push in a direction that allows gravity to continue holding them together. The new orbit is often elongated, causing the distance between the two objects to change noticeably during each revolution. At times they draw closer, at others they move farther apart, no longer following the steady rhythm the system once maintained. The center of mass shifts to a new position, the orbital period changes, and a new system forms from what remains of the old one. Within the expanding cloud of debris, this pair may be extremely difficult to recognize. One member is a star in which nuclear fusion continues, though its outer layers carry damage and material from the explosion. The other is a neutron star or black hole, so small that it nearly disappears within the glowing cloud. They no longer resemble the two stars that were born together from the original gas, yet they may continue orbiting one another through the same force of gravity that bound them when they were young. The surviving star cannot return to its state before the explosion, and the compact core cannot recover its former shape. The entire system has crossed an irreversible boundary, yet transformation does not necessarily erase every connection. In some cases, it simply changes that connection into another form, one in which a luminous star circles a dark object, and matter between them may begin a new journey. From a great distance, the survivor remains only a point of light. No one could tell with the unaided eye that its outer layers were once swept by an explosion, that the light now reaching us contains elements that once belonged to another star, or that its present velocity is the remnant of a vanished orbit. Yet that past is still present in every movement, in the way the star rotates, and in its position within the surrounding remnant. Survival in the universe rarely means returning unharmed. More often, it simply means that a structure remains strong enough to continue, even though the path ahead has been rewritten. The surviving star cannot return to the quiet orbits of the past, nor can it find its companion in the form it once knew. It can only carry those changes forward, continue to shine, and enter a new system created from the very moment the old one broke apart. After the light has passed and the ejected material has moved away, the greatest question remains within the motion of the two celestial bodies. Is gravity still strong enough to keep them together? The fact that the star has survived structurally does not reveal its entire fate. Its orbit must still be rewritten, and within the smallest differences in lost mass, remaining velocity, and the direction of the kick, a system may separate into two independent paths or continue within an entirely new orbital dance. Yet this new bond is not an unchanging state. The surviving star continues to age, expand, and alter its stellar wind. Matter may begin flowing toward the neutron star or black hole, causing the orbit to evolve once again. Each time mass passes from one side to the other, the system's center of balance shifts slightly. A post-supernova binary is not a frozen remnant, but a structure still moving through a history of its own. The outer remnant, may gradually become more diffuse, its filaments fading and blending into the space between the stars, while near the center, the two objects continue completing orbit after orbit. An observer unaware of their history might see only a bright star beside a small source of X-rays. Yet behind that point of light lies an entire past, a cloud that once gave birth to two stars, millions of years of motion, an explosion that changed the mass of the system, and a new orbit formed from everything that was not carried away. There is a distinctive kind of quietness within systems like these. They no longer carry the violence of the explosion itself, yet neither have they become completely cold and lifeless ruins. One star is still shining, the surviving core is still spinning or drawing in matter, and gravity continues to hold them along a path that may endure for immense spans of time. What makes these systems remarkable is not simply that they survived the explosion, but that they reveal how a bond can change without necessarily disappearing. The two stars no longer exist in their original forms, and the old orbit is gone, yet from that destruction, another system has emerged. It is neither a restoration of the past nor a beginning entirely separate from it, but a continuation written from what remained. If the system breaks apart, the surviving star carries its history across the galaxy as a solitary object. If the bond endures, it continues orbiting the transformed core, each revolution carrying it through a region filled with gas from the ancient explosion. Whichever path it follows, the survivor is no longer what it once was. Its velocity, surface, composition, and future have all been rewritten. Once the brightest light of the supernova has receded, these quiet changes begin telling a much longer story. A star may depart, a system may continue, and an orbit may preserve the trace of a moment that passed long ago. Within the graveyards of stars, motion is never merely something left behind. Sometimes it is the way the past continues to exist. And within the light of the surviving star, those traces have not yet completely faded. The explosion may have altered its path, but it also left deeper changes across its surface and within its structure. To find such a survivor among the countless points of light in the galaxy, astronomers must do more than trace its orbit. They must also read what the explosion left behind in its temperature, rotation rate, and chemical composition. In the light of the surviving star, the explosion has not yet become entirely part of the past. The material that once swept through the system may have traveled far away. The remnant shell may still be expanding, and the old orbit may now exist only as a trace within the star's motion. But the changes inflicted on the companion did not vanish when the most violent moment came to an end. They remain within layers of gas that were heated, in the matter that was stripped away, in an altered rotation rate, and in certain elements that do not belong to the star's ordinary history. The survivor continues to shine, but its light now carries the story of two stars rather than its own story alone. From a great distance, the difference may be almost impossible to recognize. The star still appears as a small point of light among millions of others, with no visible crack or boundary marking where the supernova debris once struck. A stellar surface does not preserve an injury the way stone or metal retains a dent. It is a layer of constantly moving plasma, where hot gas continually rises, sinks, and mixes. The clearest signs of the impact may gradually soften with time, but that does not mean all the evidence has been erased. Immediately after the explosion, the side facing the collapsed companion may have been driven inward, while other regions remained closer to their earlier state. This imbalance causes the entire star to oscillate, not like a vibrating solid object, but like an immense sphere of gas trying to recover a shape that can once again be supported by its own gravity. The outer layers may expand as they retain additional heat, making the star larger and cooler at the surface, even while its total energy output may increase. Over time, that heat gradually escapes into space. The gaseous layers contract, and the star moves toward a new state of stability. Yet this new state does not necessarily match the form it had before the explosion. The time required for the star to settle depends on the severity of the impact it endured. If the explosion removed only a relatively thin layer of gas, the change may be subtle and difficult to distinguish from other natural variations. If the star was closer, or if its outer layers were already swollen and loosely bound, the collision may have stripped away a significant amount of matter, forcing deeper adjustments within its structure. The star continues to exist, but the relationship between its core, its gaseous layers, and its surface has been rewritten by an event that came from outside. At times, this transformation can make the star's age and appearance seem mismatched. A star that has lost its outer layers may expose hotter regions from deeper within, giving it a surface color and temperature unlike what would normally be expected for a star of similar mass and age. In other cases, heat from the impact causes the gas to swell, creating a broader but cooler surface. These seemingly opposite effects are not contradictions. They reveal that each survivor responds according to the structure it possessed before the explosion arrived. Finding a surviving companion, then, is not as simple as looking toward the center of a remnant and selecting the nearest point of light. A remnant may contain many stars that lie along the same line of sight, but are actually located at very different distances. A bright point near the cloud's center may never have belonged to the original system, while the true survivor may no longer be near the center at all. It may have moved away from its former position, carrying the orbital velocity it possessed before the explosion and continuing through space for hundreds or thousands of years afterward. Astronomers must therefore assemble many different clues, like reconstructing a story after most of its opening pages have been carried away by the wind. Position is only the beginning. The star's motion, temperature, brightness, rotation rate, and the composition revealed in its light must all be considered together. No single piece of evidence is always strong enough to provide a conclusion on its own, but when several traces point toward the same past, the possibility that the star once stood beside a supernova becomes far more convincing. One of the clearest clues lies in the way the star moves. Most stars within the same region of a galaxy share relatively similar motion because they are influenced by the same large-scale gravitational field and may sometimes have formed from related regions of matter. A star traveling in a different direction or moving significantly faster will stand out from the general flow. It is like a leaf drifting with a current, but suddenly carrying a speed and direction that do not match the leaves around it. This motion is recognized in two parts. The first is the star's extremely slow shift across the background of the sky over many years, commonly known as proper motion. The distances between stars are so vast that this change appears only as a tiny angle, but precise observations made over long periods can reveal that the point of light has moved from its former position. The second part lies along our line of sight. As the star approaches Earth or recedes from it, a motion that cannot be seen directly by comparing its position in photographs. Light allows us to measure this hidden component of motion. When the star travels toward us, the lines in its spectrum shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The change is very small, but it is enough to reveal the star's velocity through the depth of space. When its motion across the sky is combined with its movement along our line of sight, the star's three-dimensional path begins to emerge, allowing astronomers to try tracing it backward toward the place where the explosion once occurred. Tracing that path does not always produce a clear result. Over long periods, the gravity of the galaxy may curve the star's trajectory, while the remnant itself continues expanding, and the geometric center of the cloud may not perfectly match the original location of the explosion. Even so, if a star is moving away from the central region at a suitable velocity, it becomes a compelling candidate. Its present trajectory then resembles a slender thread connecting the departing point of light to the place where the binary system was once broken apart. The star's rotation rate provides another thread. In many close binary systems, matter may have flowed from the larger star onto its companion before the explosion occurred. This gas does not fall straight downward. It carries orbital motion with it, transferring additional angular momentum to the receiving star and gradually causing it to spin faster. By the time its companion explodes, the surviving star may already possess an unusually high rotation rate. The later impact makes the picture even more complicated. Supernova debris strikes from one direction, while part of the star's outer layers is stripped away, carrying some of its original rotational motion with it. Depending on how the forces are distributed, the star may spin faster, slow down, or enter an oscillating state that requires a long time to settle. A high rotation rate alone, therefore, cannot prove that a star survived a supernova, but when combined with other evidence, it adds another piece to the larger picture. Light from the surface preserves an even subtler form of evidence: chemical composition. An ordinary star produces a spectrum containing absorption lines that reflect the elements within its outer atmosphere. These lines are like fingerprints, with each element leaving its own pattern at specific wavelengths. When astronomers study the spectrum of a possible survivor, they search for elements appearing in amounts that do not fit the star's normal evolutionary history. If some of the material from the explosion remains on the surface, it may carry elements that once lay deep within the companion star or were created during the final stages of the event. Over time, that material mixes with the gas already present, making the signal weaker and more difficult to interpret. But under favorable conditions, the unusual composition may remain long enough for the light to reveal that the star's surface was once coated with matter from another source. There is something remarkable in that idea. A star explodes, its outer layers are hurled away, and most of them continue expanding into space, yet a very small amount comes to rest on the companion that once orbited beside it. Hundreds or thousands of years later, human beings observe from a distant world, separate the light into bands of color, and find within it the trace of a star that no longer exists. Matter becomes a form of memory without awareness, without words, yet still preserving its origin within its atomic structure. Nature, however, rarely leaves behind a perfectly clean signature. Unusual elements may have come from mass transfer that occurred before the explosion, rather than from the supernova ejecta itself. Convection within the star can also bring material from deeper layers to the surface, creating an unusual composition without any outside influence. Identifying a survivor therefore requires caution. The most compelling evidence does not come from a single clue, but from the way several independent clues tell the same consistent story. Brightness and temperature must also be understood within that larger context. A star that appears brighter than expected may still be releasing energy absorbed during the impact. A fainter star may have lost part of its outer envelope or had its structure altered in another way. Computer models help scientists imagine how a star might respond when struck by supernova debris, and then compare those predictions with the light actually observed. A model is not an exact image of the past, but it creates possibilities that can be tested against the data. In this way, a survivor gradually emerges, not as a star wounded in the way we might usually imagine, but as a system displaced from its former state and carrying a long-lasting adjustment. Its outer layers may have changed, its rotation may no longer be the same, and its orbit may have opened into a solitary path or closed around a compact object. Every feature it possesses in the present is the layered result of its own stellar life and the history it once shared with its companion. Such a star may continue living for a very long time. It still fuses hydrogen into helium, still shines, and still ages according to the general laws that govern stars. The explosion does not stop its passage through time. It only changes the starting point of the life that remains. From that moment forward, every new transformation unfolds within a star that has lost some matter, gained certain elements, and may be carrying a velocity it would never have possessed if the binary system had remained intact. If the orbit continues to hold the two objects together, the story follows another path. The surviving star keeps circling the neutron star or black hole, and that continued closeness can create new forms of activity. stellar wind flowing outward may be captured by the compact object. As the star grows older and expands, gas from its outer layers may begin crossing the space between them. A system already transformed by the explosion starts producing streams of matter and sources of energy that never existed in its original form. But before those streams become a luminous bridge between the survivor and the remaining core, we must move beyond a fundamental limit in the way we observe the universe. Visible light shows us the star's surface and the regions of gas able to shine within the familiar range of colors. Many of the most powerful processes inside a remnant, however, are hidden at wavelengths the human eye cannot detect at all. A surviving star may be recognized through its own light, but neutron stars, extremely hot gas, and matter falling into a region of intense gravity often tell their stories through a different kind of light. In ordinary images, they may disappear among dust, gas, and countless points of starlight. Only when we lift artificial senses above Earth's atmosphere do stellar graveyards begin to reveal the sources of energy hidden deep within them. There, an entirely different sky waits to be opened. It contains none of the colors familiar to human vision, yet it glows with hot gas, rapidly moving particles, and small objects quietly gathering matter. To understand why a remnant that appears calm can change in brightness over the years, we must learn to see the universe through light that will never reach the retina of the human eye. Visible light is only a very small part of what the universe sends our way. It is enough to reveal stars, glowing clouds, and delicate filaments of gas within supernova remnants, yet many of the most powerful processes unfold at wavelengths entirely beyond the reach of human vision. A region of space may appear almost quiet in familiar light, while in another form of light, it contains intensely hot gas, streams of fast-moving particles, and small sources of energy changing from day to day. This does not mean that human eyes see the universe incorrectly. It simply means that our senses evolved for life beneath the light of the sun and within the environment of Earth, not for detecting everything that can exist across the cosmos. The retina responds to only a narrow portion of the electromagnetic spectrum. On either side of that range lie many other forms of light, from long, gentle radio waves to extremely energetic gamma rays. Each kind of light interacts with matter differently, and each one therefore opens a different layer of the same sky. For this journey, the most important of these forms is X-ray light. On Earth, the name often brings to mind a hospital image, where X-rays pass through soft tissue and reveal the structure of bones inside the body. In astronomy, X-rays play a similar role. They do more than show the beautiful, luminous surfaces of celestial objects. They help uncover regions of extreme heat, powerful collisions, and matter moving near objects with exceptionally strong gravity. X-rays are a form of light, but each X-ray photon carries far more energy than a photon in the visible range. They are often produced when matter is heated to extremely high temperatures, or when charged particles move through harsh and energetic environments. Ordinary cold, diffuse gas between the stars does not emit strong X-rays, but when a supernova shock wave sweeps through, compressing and heating the gas to millions of degrees, that region can begin to glow in X-rays even though the human eye sees no color coming from it at all. This is why a supernova remnant can present two very different faces. In visible light, we may see thin filaments of gas, curved arcs, or glowing regions where atoms have been excited. In X-rays, a broader layer of hot gas appears, sometimes filling much of the structure's interior. These two images do not contradict one another. They simply reveal different states of matter, existing together within the same region of space. If visible light is like seeing mist illuminated from the outside, X-rays are closer to sensing the regions that still hold heat deep within. A cloud may appear thin and delicate in an optical image, yet behind those bright filaments lies matter so hot that atoms can no longer hold on to their electrons in the ordinary way. This highly ionized state creates the signatures that X-ray telescopes are able to detect. X-rays from space, however, do not easily reach the ground. Earth's atmosphere absorbs most of this radiation before it reaches the surface, and that is fortunate for life. The layer of gas surrounding our planet acts as a shield, preventing many forms of high-energy radiation from penetrating deeply into the environment where humans and other living things exist. But this same protection also means astronomers cannot place an X-ray telescope on a mountain and observe the sky as they would in visible light. To see the universe in X-rays, instruments must be carried above most of the atmosphere. Observatories placed in orbit around Earth become artificial senses, operating where cosmic X-rays can still reach them. They do not create colors in the way human eyes do, nor do they take pictures exactly like an ordinary camera. Instead, they record the energies and positions of individual X-ray photons. From those signals, scientists construct images that reveal which regions are hotter, brighter, or changing over time. One of the most important observatories for this work is Chandra. It was designed to observe the X-ray universe with enough sharpness to separate small sources of light from complex regions of hot gas. Its name may appear many times in the story of stellar graveyards, but what matters is not a list of instruments or technical specifications. What matters is the way Chandra allows us to see phenomena that disappear completely in ordinary light. When Chandra is directed toward a supernova remnant, it can detect X-rays from gas heated by shock waves, from high-energy particles, or from a compact object buried deep within the cloud. A tiny neutron star may be almost completely lost inside a structure spanning many light-years. But if it emits X-rays or heats the material around it, that small source may stand out more clearly in high-energy data. A black hole does not shine on its own, but gas pulled close to it can become intensely hot, revealing the dark object's location through the light produced in its surroundings. This completely changes the way we imagine a stellar graveyard. An optical image may make a remnant look like an expanding shell, while an X-ray image reveals that the interior is far from empty. Hot gas may fill regions that appear dark. A small point of light may sit away from the center. An area that seemed quiet may be releasing far more energy than everything around it. Astronomers do not need to see the surface of a neutron star or black hole directly. They can recognize its presence through the way nearby matter glows. A single image, however, can tell us only that an X-ray source exists at the time of observation. It cannot yet reveal whether that source is stable or changing, nor can it always separate light coming from hot gas from light produced by matter falling toward a compact object. To understand what is truly happening, astronomers must return to the same region again and again, sometimes with years between observations. This is where astronomy becomes an exercise in patience. The universe does not change according to the pace human beings might prefer, and many sources reveal their nature only after being observed over long periods. One observation may show only a point of light. A second makes comparison possible. When many observations are placed side by side, that point may reveal that it has grown brighter, become fainter, or changed in a way that does not fit a cloud of gas slowly cooling over time. We might imagine a house so far away that it appears only as a tiny point in the darkness. If we look once, we know only that a light is present. But if we return on many different nights and see the light turning on, turning off, or changing in intensity, we begin to understand that some activity is taking place inside. We may not know who is there or what is producing the light, but the variation alone is enough to rule out the idea of a lamp that never changes. Variations in X-ray light within supernova remnants carry a similar meaning. Expanding hot gas usually changes at a relatively slow pace. It may brighten when a shock wave encounters a denser region of matter, or fade as the gas expands and cools, but these changes are generally connected to the remnant's larger structure. A small source that changes dramatically over a shorter period may suggest that matter is being drawn toward a neutron star or black hole, where an unstable flow creates intervals of greater brightness, followed by quieter phases. Even so, every unusual point of light must be examined carefully. A galaxy contains many X-ray sources unrelated to any particular supernova remnant. There may be X-ray binary systems, active galactic nuclei, or much more distant objects that happen to appear along the same line of sight. The fact that a source appears close to a remnant in an image is not enough to prove that it belongs there. Astronomers must compare its position, energy spectrum, degree of variability, and signatures at other wavelengths to understand what the source truly is. It is precisely this caution that gives such discoveries their value. Science does not choose an appealing explanation and simply stop there. It must test whether that explanation fits every available clue, while also considering other processes that could produce the same signal. In stellar graveyards, a changing X-ray source may come from a surviving companion, transferring matter to a compact core, but it may also be associated with shocked gas, material falling back toward the center, or an unrelated source beyond the remnant. Observing in X-rays is therefore like opening a door into a dark room, but the open door does not automatically explain everything inside. It only allows us to see that the room contains more structure than ordinary light had revealed. The remaining work is to bring together position, time, energy, and motion in order to understand what is creating each bright region. X-ray images also do not contain color in the way human eyes would perceive it if we could stand near the object. Because X-rays lie outside the visible range, scientists assign colors to different energy levels so the data can be read more easily. One color may represent lower energy X-rays, another may represent higher energy radiation, or each color may correspond to a different kind of observation. These vivid images are therefore both scientific data and a way of translating invisible light into a visual language that human beings can understand. This does not make the images artificial. It simply means that color is carrying information rather than reproducing exactly what the eye would experience. In the same way that an elevation map uses green, yellow, and red to distinguish low regions from high ones, an X-ray image uses color to help us recognize where matter is hotter, more energetic, or different in composition. The universe does not need to appear the way human eyes see in order to be real. When these data are placed alongside optical, infrared, and radio images, a supernova remnant begins to reveal itself as a layered environment. The outer shell carries the marks of shock waves, dust glows in infrared light, high-energy electrons leave signals at radio wavelengths, extremely hot gas appears in X-rays. Near the center, a tiny point of light may be the compact core or a binary system that survived the explosion. But what makes the story remarkable is not simply that an X-ray source may be hidden inside the remnant. More striking is the fact that some of these sources refuse to maintain a constant brightness. They brighten, fade, and change in ways that force astronomers to reconsider what was once thought to be merely a cloud quietly cooling over time. Recognizing this requires many years of observations and a place rich enough in supernova remnants to provide a clear picture. That place is not within our own Milky Way, but in a distant spiral galaxy where regions of star formation remain highly active and many massive stars have left behind glowing shells. That galaxy is M83. In visible light images, M83 appears with graceful spiral arms and brilliant regions of young stars. But when Chandra observes it in X-rays, many small points of light emerge among those spiral arms, each potentially arising from a different source. Some remain almost unchanged over time, while others vary strongly enough to suggest that active systems are still operating inside remnants that otherwise appear quiet. When observations separated by many years are placed side by side, the stellar graveyard is no longer a static image. It becomes a region of space with a rhythm of its own, where a point of light may grow brighter and then fade, where a surviving star may still be transferring matter to the compact core left behind, and where the death of one star has not brought the entire system into silence. It is within these points of light that refuse to remain still that the secret life of stellar graveyards begins to emerge more clearly, not through colors visible to the human eye, but through high-energy light that has traveled across millions of years of space, reached a telescope above Earth's atmosphere, and carried a quiet message from a place that seemed to have ended. Something there is still changing. About 15 million light-years from Earth, M83 appears as a vast spiral galaxy, presenting nearly its full face toward us. Bright arms curve around the central region, threaded with dark lanes of dust and many clouds of gas where new stars are still forming. In visible light, it looks graceful and almost symmetrical, like a whirlpool held in place within space. But when that same sky is viewed in X-rays, the sense of stillness begins to change. Numerous small points of light appear along the spiral arms, each potentially representing hot gas, an active binary system, or the remains of a star that exploded long ago. M83 is especially well suited to the search for such remnants, because the galaxy is still producing many massive stars. Large stars live brilliant but relatively brief lives, so wherever young generations of stars are abundant, there is also a greater chance of finding traces of explosions that occurred in the comparatively recent past. Among the glowing clouds and young star clusters, astronomers have identified many X-ray sources whose positions and characteristics are consistent with supernova remnants. At first, they were viewed as clouds of hot gas left behind by earlier explosions, still expanding and slowly losing energy. That is generally what we expect from a remnant that has existed for long enough. Its shock wave continues moving outward. The gas gradually becomes more diffuse, heat disperses, and the X-ray emission should, overall, decline at a relatively slow pace. Small changes may occur when the shock wave enters a denser region of gas, or when the internal structure continues to adjust, but a cloud spanning several light years would not normally brighten and fade rapidly like a small active source. For that reason, when the first observations were made, no one expected these remnants to display such strong and obvious variability. Chandra first observed M83 in 2000, then returned in 2001. A decade later, the galaxy was monitored several times between 2010 and 2011, followed by another observation in 2014. These visits did not create a continuous movie. They were more like individual frames, preserved at times separated by months or years, each recording the state of the X-ray sources during a brief interval. Yet when those frames were placed side by side, time began to reveal differences that no single observation could ever have shown. Imagine a distant city viewed from above on different nights. During the first visit, we see thousands of illuminated windows, but we do not yet know which lights are steady and which have only just been switched on. When we return a year later, and then again many years after that, some windows remain almost unchanged, while others grow brighter, become faint, or nearly disappear. We still cannot see what is happening inside each room, but the changing light is enough to tell us that they are not all the same. The X-ray points in M83 began telling their story in much the same way. When researchers compared data spanning 14 years, they found that many sources previously classified as supernova remnants did not simply fade along a smooth and gradual path. Some changed noticeably, sometimes growing stronger and sometimes becoming weaker, as though a smaller structure with its own rhythm of activity were hidden inside the expanding debris. The surprise was not merely that one source varied, since the X-ray universe contains many objects with unstable brightness. What made the result difficult to ignore was the number of sources showing the same kind of behavior. Among a sample of 22 X-ray sources associated with remnants, about half showed significant changes in brightness during the period of observation. This no longer resembled a rare exception discovered by chance. It suggested that M83 might contain an entire population of objects that had not yet been fully recognized. These sources had been present in the data all along, but only when time itself was used as an observational tool did their unusual nature begin to emerge. One of these cases has a relatively straightforward explanation. The remnant known as SN 1957D came from an explosion observed in 1957, and its shock wave is still colliding with material around the site of the event. When that disturbance encounters denser regions of gas, the X-ray emission can increase, producing episodes of greater brightness without requiring a hidden binary system. But that explanation cannot be applied to all the remaining sources. There is no evidence that every one of them is a young remnant undergoing similar collisions within the same recent interval. Another cause seems to lie behind the changing points of light, and it brings us back to the journey of two stars that once shared an orbit. The more massive star exploded, leaving behind a neutron star or black hole. Its companion survived, was not completely ejected from the system, and remained bound within a new orbit. What had once been only a possibility in the evolution of binary stars was now appearing before us as a population of variable X-ray sources. If this explanation is correct, each point of light contains more than a cooling cloud of gas. There may also be a star still sustaining nuclear fusion, orbiting the compact core of its former companion. The explosion happened long ago, and the outer remnant continues to expand, but the two objects near the center have not stopped influencing one another. The surviving star releases gas into space, or allows some of its outer material to be drawn toward the neutron star or black hole. As that matter enters a region of intense gravity, it heats up and emits X-rays, causing the source to brighten and fade as the flow changes in an unstable way. M83 is too distant for Chandra to separate the broad gas cloud of a remnant from a small binary system hidden inside it. In an image, the two may blend into the same X-ray point, even though their true sizes differ enormously. A remnant can stretch across several light-years, while the region of infalling matter around a neutron star or black hole is vastly smaller. But across a distance of 15 million light-years, those structures overlap within the same part of the image, like a small lamp seen through a wide layer of mist that we cannot approach closely enough to separate. Variability in brightness, therefore, becomes the clue that helps distinguish them. A large cloud of gas cannot easily change dramatically over a short period, while the flow of matter near a compact object may thicken or thin, become interrupted, and then begin again. Every change in that flow alters the amount of X-ray light being produced. The source is no longer merely a passive trace of an ancient explosion. It may be creating new light within the system's present moment. This gives the remnants in M83 a meaning different from what their appearance first suggests. They are not only places where stars came to an end, but may also be broad shells surrounding bonds that continue to exist. Farther out, hot gas slowly spreads through the galaxy. Near the center, a surviving star continues moving around a neutron star or black hole. Between the two objects, gravity begins gathering matter into narrow streams invisible to human eyes, yet recognizable to Chandra through changes in X-ray brightness. Here, the question that has followed us from the beginning starts to receive a clearer answer. After a star explodes, the material thrown outward is not the only thing that continues moving through the darkness. There may still be a closed orbit, a star that continues to shine, and a compact core drawing gas toward itself. The secret life of a stellar graveyard does not lie in an unknown organism, but in physical systems that remain active after their original form has disappeared. Even so, science cannot stop at the most compelling explanation. The distance of M83 limits the detail telescopes can resolve, so no individual point of light can yet be identified with complete certainty as a system containing a surviving star. Some sources may indeed be X-ray binaries, still embedded within remnants. Others may brighten because shock waves are striking dense material. It is also possible that the compact core is drawing back some of the matter expelled by the explosion itself. The important point is that these sources do not all need to share the same cause. A large galaxy can contain many different stories within a single set of observations. In one place, a companion star may be feeding gas to a black hole. Somewhere else, Material from the explosion may be falling back toward a neutron star. Another remnant may simply be encountering a dense cloud as it expands. Similar brightness does not require every source to have the same history. Still, the presence of many variable sources in regions rich with massive stars makes a connection to binary systems especially noteworthy. Such regions are where two massive stars may be born together, where one member dies earlier, and where the survivor may still be large enough to provide a powerful flow of gas after the explosion. The environment does not directly prove the nature of each individual case, but it makes the broader picture more consistent with the journey we have just followed. A later study of M51, another galaxy with vigorous star formation, revealed a similar population of variable X-ray sources associated with supernova remnants. This suggests that M83 may not be entirely unique. Surviving systems like these may exist in many galaxies, only beginning to reveal themselves when the data are monitored for long enough and viewed in the right kind of light. Thousands of remnants once regarded simply as cooling clouds of gas may still contain far more activity than a static image can show. Some may hold neutron stars spinning quietly within them. Some may conceal black holes that produce no light of their own. Others may still contain companion stars slowly losing matter into the gravitational field nearby. The universe has not changed its nature because we have only now discovered this. It is simply our view that has become more complete. If M83 had been observed only once, those X-ray points would have told us very little. They lie among countless other sources of light, so small that they seem to possess almost no individual character. But when 14 years of observations are placed side by side, a quiet rhythm begins to emerge. The light rises and falls not quickly enough to seem chaotic, but clearly enough to show that these remnants do not all follow the simple fading path once expected of them. At this point in our journey, we can pause and look back at the path we have followed. A massive star forms from cold gas, lives through a balance between gravity and energy, and then collapses when its core can no longer support itself. The explosion leaves behind expanding matter, a compact core, and sometimes a surviving companion. The orbit may break apart or continue, while the remaining star carries chemical and dynamical traces of the event. In M83, all of these layers come together within one very small signal, an X-ray point that refuses to remain at the same brightness. That point of light does not tell us on its own where the matter is coming from or where it is going. It reveals only that energy is being produced in a changing rhythm. To understand more deeply, we must enter the space between the surviving star and the compact core, where gas no longer belongs entirely to either one and begins to form a new stream. From such a great distance, that flow of matter cannot be seen as a clearly defined ribbon of light. But within the gravitational field of a neutron star or black hole, it heats up, spirals faster, and transforms motion into X-rays. It may be the invisible bridge connecting the survivor to what remains of its former companion, allowing the stellar graveyard to keep shining long after the original explosion has faded into the past. From a great distance, the space between the surviving star and the compact core of its former companion appears almost completely dark. The two objects orbit one another along their new path, sometimes drawing closer and sometimes moving farther apart, while the outer remnant continues to expand and fade. There is no clearly visible bridge connecting them, and no boundary marking the point where matter begins to leave one side and travel toward the other. Yet, within that seemingly empty space, a new flow can begin to form, slowly drawing material away from the living star and carrying it toward the neutron star or black hole. The surviving star does not hold on to all of its gas forever. Even without a nearby companion, stars continually release matter into space in the form of stellar wind. This is not wind in the familiar earthly sense, because there is no surrounding atmosphere to carry motion from place to place. A stellar wind is a stream of charged particles escaping from the outer layers, driven outward by the star's own radiation, heat, and magnetic fields. In some stars, this flow is relatively gentle. In massive, luminous stars, it can be powerful enough to carry a significant amount of material away from the surface over long periods of time, allowing it to blend into the surrounding space. In an ordinary binary system, most of that stellar wind may continue drifting away without being captured. But when a neutron star or black hole lies nearby, part of the gas enters the compact object's gravitational reach. It does not need to be launched directly toward the companion. As long as some of the wind passes close enough and is not moving too quickly, its path begins to curve. Matter that was leaving the surviving star in many directions is gradually gathered inward, like drifting grains of dust suddenly entering an invisible vortex. This process does not create a perfectly steady stream. Stellar winds can change with the activity of the star, its magnetic field, and denser regions of gas that form within its outer layers. An elongated orbit also causes the distance between the two objects to change continually. When the neutron star or black hole approaches the surviving star, it passes through denser gas and may capture more material. As it moves farther away, the flow reaching it becomes thinner. The invisible bridge between the two bodies may therefore strengthen and weaken with every orbit, even though from a distance we see only a tiny point of light changing over time. We might imagine the star releasing a faint mist around itself. Most of that mist continues spreading into space, but the presence of the compact object pulls one region out of symmetry, creating a flow that leans toward it. There are no clearly defined banks like those of a river, only a gradual increase in gas density along the direction in which matter is being captured. Each particle follows its own path, but when countless particles are bent by gravity together, they form a stream large enough to change the way the entire system shines. Stellar wind is not the only path. As the surviving star continues to age, its outer layers may expand. This increase in size does more than bring the surface closer to the compact object. It also pushes some of the gas into a region where the gravity of the two bodies competes more directly. Close to the star, matter remains bound by its own gravity. Farther from the surface, however, that hold becomes weaker, and within a particular region between the two objects, even a small disturbance may keep the gas from returning to the star it came from. The gravitational regions surrounding each member can be imagined as a domain in which matter tends to belong to that object. As long as the surviving star remains small compared with its own gravitational domain, its outer gas stays safely inside. But if the star expands far enough, its surface approaches the boundary between the two regions. Matter on the side facing the neutron star or black hole may then cross the balance point and begin flowing toward the other object. This stream differs from a stellar wind. A wind leaves the surface in many directions, with only part of it later being captured, while gas overflowing through the gravitational boundary tends to be more concentrated. It resembles a narrow ribbon of matter stretching from the surviving star toward its companion, sustained by the difference in gravity and by the motion of the system itself. In most systems, this bridge is far too small to be seen directly from a great distance, but its effects can be far greater than its appearance suggests. It carries mass, momentum, and energy, gradually changing both objects at either end. The surviving star is therefore not simply losing its outer gas. Every amount of matter that leaves forces its internal structure to adjust. If the process continues long enough, deeper layers may be exposed, changing the star's temperature, size, and rate of evolution. The compact object on the other side does not merely receive additional mass passively. The incoming gas carries the motion of the orbit with it, which means it rarely falls straight toward the center along a simple path. This is where everyday intuition can easily mislead us. When we think of the powerful gravity of a neutron star or black hole, we may imagine nearby matter plunging directly inward, like a stone falling toward the ground. But the gas in a binary system already carries sideways velocity from its orbital motion. It is not standing still before gravity begins to draw it in, and so instead of falling directly, the material usually circles around the central object. Each particle is pulled inward, while also trying to continue along its original direction. Its path therefore bends, wraps around the neutron star or black hole, and gradually forms a swirling structure. New matter continues entering from farther out, while material already inside moves faster as it approaches the center. Not every system forms the same clearly defined structure, since the result also depends on the amount of matter, its velocity, and the magnetic field. Even so, swirling motion is a natural outcome whenever the incoming gas carries angular momentum. The bridge of matter does not end at the compact object itself. It opens into a layered region of motion, where gas from the surviving star continues to orbit, collide, and slowly drift inward. From a relatively narrow stream flowing between the two members, the material gradually spreads into a swirling structure around the remaining core. The closer it moves toward the center, the smaller its orbit becomes, the faster it travels, and the more its surroundings differ from the environment it left behind near the original star. If the core is a neutron star, the material may eventually reach a true surface, where matter exists at an extreme density. A powerful magnetic field can guide the gas toward particular regions near the poles, preventing the flow from being distributed evenly. If the core is a black hole, there is no solid surface for the material to strike in the same way. The gas continues deeper inward, and once it crosses a certain boundary, it can no longer send information back to the outside. But before reaching that final region, the material has already passed through a journey intense enough to release an enormous amount of energy. A black hole, however, does not pull everything in space toward itself without limit. A star at a sufficient distance can orbit it steadily, just as planets orbit the Sun. Only material that leaves the star and enters the right region can be captured. Distance, velocity, and direction of motion still determine whether it escapes, remains in a wide orbit, or gradually moves inward. Understanding this makes the bridge of matter far more subtle. It is not a flow created simply because a black hole or neutron star sucks in everything around it. It is the result of the entire system. The surviving star releases gas. The orbit carries the two objects through changing distances. Gravity bends the paths of the particles, and the motion they already possess causes them to spiral rather than fall straight inward. No single factor acts alone, and it is this combination that creates the variable source of light observed from so far away. The flow of matter does not necessarily remain at the same rate. The outer layers of the star may pulsate, the stellar wind may strengthen or weaken, and the orbit may carry the compact object through regions of gas with different densities. Within the swirling structure, material may sometimes accumulate before continuing inward, causing the amount of gas near the center to change over time. Each of these variations can make the emitted energy rise or fall. For this reason, an X-ray point in M83 may appear brighter during one observation and much fainter years later, not because the entire remnant has changed, but because the small bridge of matter near its center is carrying a different amount of gas. What Chandra sees is only the final result of a flow too distant to observe directly. The changing light becomes evidence of gas traveling from the surviving star toward the transformed core of its former companion. There is a quietness to this process. The star does not lose its matter in a single moment, but allows it to leave in thin layers over time. The neutron star, or black hole, does not need to produce light of its own, because the approaching gas is enough to reveal its presence. Between the two celestial bodies, matter continually changes hands, carrying the history of the surviving star into an environment where gravity will transform it far more profoundly. The outer remnant continues to expand, carrying the story of the explosion farther from the central region. Yet inside that shell, the narrow bridge of gas is creating a different story, one that is slower and more persistent. It connects a star that is still alive to the core of a star that has died, allowing two seemingly opposite states to continue shaping one another within the same system. From matter leaving the surface to gas whose path is bent by gravity, From the narrow bridge between the two members to the vortex surrounding the compact object, each stage removes some of the energy from the motion. The gas collides, becomes compressed, and enters progressively smaller orbits. What begins as a thin wind around the star may end in a region so hot that it no longer shines mainly in visible light. It is there that the invisible bridge begins to become light. Not because matter suddenly ignites when it approaches a dark object, but because gravity is drawing it deeper, making it move faster and release energy along the way. To understand how such a small amount of gas can cause the entire system to shine brightly in X-rays, we must enter that vortex where the motion of matter is being transformed into heat and light before it reaches the final point of its journey. The bridge of matter between the two celestial bodies does not end when the stream of gas reaches the gravitational influence of the neutron star or black hole. From there, it begins a different journey, one in which every orbit carries the material closer to the remaining core of the dead star. The gas that once left the surface of the survivor is no longer drifting freely. It is captured, curved, and drawn into ever smaller spirals, like a thin ribbon of mist, slowly winding around a dark center that human eyes cannot see. The material does not fall straight inward because it still carries motion from the orbit of the entire system. While gravity pulls it toward the center, its sideways velocity keeps the gas circling the central object. The outer layers move along wider paths, while gas that has traveled closer must move faster to avoid falling inward immediately. The entire structure therefore becomes a layered vortex, where matter both circles the center and gradually drifts deeper within. From our distance, this motion is completely invisible. But inside the vortex, the gas does not pass quietly from one region to another. Different layers move at different speeds, continually pressing, pulling, and disturbing one another. The material gradually loses the energy that keeps it in a wide orbit and shifts into smaller paths, where the motion is faster and the gravitational field is stronger. The energy it loses does not disappear. It is converted into heat, making the gas increasingly hotter as it approaches the center. We might picture water spiraling into a funnel, though every comparison on Earth is small beside what unfolds around a compact object. Water near the edge follows a broad, slow path, but as it approaches the opening, the circle narrows and the speed increases. Matter around a neutron star or black hole undergoes a similar transformation, but within a far deeper gravitational field, where the gas is heated until it no longer shines mainly in the colors familiar to human vision. When the temperature rises high enough, atoms can no longer maintain their ordinary structure. Electrons separate from their nuclei, and the matter becomes a hot plasma, filled with charged particles continually moving, colliding, and interacting with magnetic fields. It is this environment that produces X-rays. The light detected by Chandra does not necessarily come from the neutron star or black hole itself, but from matter losing energy as it travels toward them. This explains how such a small region can stand out within a remnant spanning many light years. The outer cloud contains far more mass, but it has spread across an enormous volume and changes relatively slowly. The accreting region near the center concentrates energy into a much smaller space, where every portion of matter can release a great deal of energy as it falls deeper into the gravitational field. An X-ray point in an image may therefore contain an entire flow of hot, complex material, even though its true dimensions are far too small for the telescope to resolve into a clear shape. If the object at the center is a neutron star, the gas may eventually reach a real surface. A neutron star is extremely small, but contains an enormous amount of mass, so matter falling onto its surface can reach tremendous speeds. Magnetic fields may guide the gas towards certain regions near the two poles, creating hotspots that emit X-rays. As the neutron star rotates, these luminous regions move with it, sometimes sending regular pulses toward Earth like the beam of a lighthouse in the distant darkness. If the central object is a black hole, the material encounters no surface to strike. It continues spiraling inward until it crosses a boundary beyond which light can no longer return. But most of the signal we observe is created before the gas reaches that boundary. The black hole itself remains dark, while the matter around it becomes bright as it releases energy during its final orbits. An object that produces no light of its own can therefore still be recognized through the activity surrounding it. Just as a stone submerged beneath water may reveal itself only through the currents above, a neutron star or black hole can be found through the hot gas moving within its gravitational field. The light does not come from a star shining through nuclear fusion, but from external matter being drawn inward and continually changing its state. This flow is rarely perfectly steady. The surviving star does not release the same amount of gas at every moment. Its stellar wind may contain denser regions, larger clumps of matter, or thinner gaps. If the orbit is elongated, the distance between the two objects also changes with every revolution, carrying the compact core through denser gas at some times and into more diffuse regions at others. Within the vortex, the gas does not move inward at a constant pace either. At times, matter gathers in the outer regions, waiting to lose more energy before drifting deeper. At other times, a larger amount of gas enters the central region at once, causing the X-ray emission to rise sharply for a while. When the supply weakens, the vortex becomes fainter. From a great distance, all of these complex changes are compressed into a single point of light that grows stronger and weaker within the remnant. This is why the variability observed in M83 is so important. An expanding cloud of hot gas may brighten or fade, but it usually does so according to the slow rhythm of a very large structure. The region of matter near a neutron star or black hole is far smaller and can respond more quickly to changes in the gas flow. When the supply of matter increases, the X-rays grow stronger. When the flow weakens, the source becomes quieter. The changing light becomes evidence of a process unfolding in the present rather than merely the passive echo of an ancient explosion. Not every variation repeats in a clear cycle. A stellar wind is not a smooth, uniform flow of gas, and the vortex around a compact object contains disturbances of its own. A powerful flare may never return in exactly the same way. Some sources remain quiet for long periods before suddenly becoming active, while others change more gradually. It is this irregularity that requires astronomers to observe them over many years before the true behavior of the system begins to emerge. However the brightness changes, the source of the energy begins in the same place, matter falling deeper into a gravitational field. Gravity does not create energy from nothing. It allows the energy associated with the gas's position and motion to be released as its path grows tighter. Much as an object falling from a height can transform the energy of its position into speed and then heat upon impact, gas around a compact object converts its inward fall into heat and light, only on a vastly greater scale. In a binary system that survives a supernova, the remaining star becomes the source of material for this process. Some of its outer gas escapes, crosses the space between the two objects, and begins to shine as it approaches the core of its former companion. The two stars once shone together through nuclear fusion, but now only one continues producing that familiar kind of light. The other reveals itself through the matter being drawn toward it. In this way, X-ray light carries information about both ends of the system. It reveals the gravitational field of the compact core, but it also reflects the stellar wind, outer layers, and orbit of the survivor. When the X-ray source changes, the cause may have begun far from the central region, where the star has just released more gas or where the distance between the two objects has recently grown smaller. Outside, the remnant continues its quiet expansion. Inside, the small vortex near the center may brighten and fade on a much faster rhythm. These two motions coexist within the same stellar graveyard, a cloud gradually dissolving into the galaxy, and a source of energy still being fed by matter from the living star. One tells the story of an explosion that has already passed, while the other reveals that the connection between the two objects has not yet come to an end. But the bridge from the surviving star is not the only path that can carry matter back toward the compact core. During the explosion, most of the outer gas is thrown outward, yet not every fragment receives enough speed to escape forever. Some material moves away from the central region, slows within the gravitational field, and eventually begins to return. In that case, the X-ray light is not powered by the living star, but by the dead star's own matter falling back toward the place it once left behind. Within the expanding remnant, some fragments of ash may quietly reverse direction and begin a long descent toward the neutron star or black hole at the center. To distinguish between these possibilities, astronomers must look for additional clues. If a bright star lies near the X-ray source, moves as part of the same system, and carries the characteristics of a survivor, then mass transfer from a companion becomes a more compelling explanation. If no suitable star can be found, or if the X-ray source lies within a very young remnant, fallback material may be the more reasonable possibility. Even so, great distance and obscuring dust mean that the evidence is not always clear enough to favor a single explanation. That uncertainty does not make the story any less valuable. It simply reminds us that the light from one tiny point can be produced through several different paths, and that science must slowly eliminate each possibility rather than immediately choosing the most appealing answer. A surviving stellar system creates a powerful image, but nature is under no obligation to make every X-ray source follow the same story. Some remnants contain companion stars, others hold only a compact core and returning material. In still others, several processes may unfold during different stages. Fallback material can also affect the core to which it returns. If the core is a neutron star, the captured gas adds a small amount of mass and may influence its rotation rate or the magnetic field near its surface. If the core is a black hole, the matter continues farther inward after releasing light in the surrounding region. In both cases, the stream of gas does more than produce a signal for distant observers. It also continues changing the central object over time. This process, however, does not necessarily continue forever at the same intensity. Once the fragments most likely to return have been captured, the supply gradually declines. The rest of the remnant keeps expanding outward and becomes increasingly difficult to draw back. The X-ray source may grow weaker, leaving the compact core quieter and harder to detect within the enormous cloud. Some compact objects may have passed through a period of intense activity shortly after the explosion, then faded before human beings ever had the opportunity to observe them. What telescopes see today is only one stage in that much longer history. A source that is bright now has not necessarily always been bright, and a core that appears quiet today may once have been surrounded by a stream of intensely hot matter. Time, therefore, becomes another kind of veil. Dust and gas are not the only things that prevent us from seeing the central region clearly. The fact that we observe it at only one moment also limits how much of its story we can know. To understand an X-ray source, astronomers must work backward from its present state, considering the age of the remnant, the amount of surrounding material, and the way its brightness changes across repeated observations. Amid these measurements, the image of matter returning still carries a quiet beauty. There is no sound, no brilliant rain visible to the human eye, only clouds of gas following slow, curved paths through the darkness. They were once driven outward by one of nature's most powerful events, yet they did not carry enough energy to escape the gravity of the remaining core. Over time, their outward motion comes to an end, and their direction silently reverses. The remnant continues expanding, making the whole structure appear to be moving away from the center. Yet within that larger outward flow, a small amount of material travels in the opposite direction. Both motions exist at once. Most of the gas moves outward into the galaxy, while some returns to the place where the star collapsed. A stellar graveyard, therefore, contains not only layers of matter dispersing into space, but also returning streams that continue feeding the central region with fragments of the past. If the material falls toward a neutron star, the compact core may begin to reveal itself more clearly through its light and rotation. Beneath the hot gas, the neutron star remains an extraordinarily small and dense object, capable of carrying an immensely powerful magnetic field. In some cases, it does not need infalling matter to produce a signal. Its rotation and magnetic field alone can transform it into a source of light with a steady rhythm. Within the expanding cloud, a tiny object may send out repeating beams of radiation with every turn, like a lamp hidden in fog that still sweeps its light regularly across space. After the chaotic flows of matter and the unpredictable changes in brightness, this rotating signal introduces a different kind of activity, more regular, more precise, and capable of enduring long after the explosion has passed. Among the layers of gas still expanding after the explosion, the star's surviving core may remain hidden like a tiny point in the darkness. Compared with a remnant stretching across many light years, it nearly disappears from view. Yet within that small object lies an enormous amount of compressed matter, along with rotation and magnetic fields that can endure long after the star's former shape is gone. If the collapse stops before forming a black hole, the core may become a neutron star, an object only about as wide as a city but containing more mass than the Sunday. Matter that once extended across hundreds of thousands of kilometers is now compressed into a space so small that its state no longer resembles anything familiar on Earth. A neutron star is not only extraordinarily dense, it may also rotate very rapidly, because the star's core was already spinning before the explosion. As the core contracts, that motion does not disappear. Instead, it is concentrated into a much smaller space, much like a figure skater spinning faster after drawing their arms closer to the body. An object that once occupied the center of an enormous star may now complete many rotations within a very short time, and that rhythm becomes one of the clearest signatures of the core left behind. Surrounding the neutron star is a powerful magnetic field, compressed and reorganized during the collapse. This field guides charged particles around the object, especially near the magnetic poles, where they may be accelerated and produce narrow beams of radiation directed into space. The axis of these beams is usually not perfectly aligned with the axis of rotation. As the neutron star spins, the beams sweep through broad circles, like the light from a lighthouse turning over a dark sea. If one of those beams happens to pass across Earth, a telescope receives a brief signal, followed by another after each rotation in a rhythm that is almost perfectly precise. Objects like these are called pulsars. They do not truly brighten and go dark with every pulse, because the source of radiation remains active continuously. What changes is the direction in which the beam is pointing as the star rotates. An observer receives the signal only when the beam sweeps across their position, causing a steady source to appear as a sequence of separate flashes. Within a supernova remnant, filled with curving streams of gas, regions of hot matter, and chaotic motion, the rhythm of a pulsar creates a very different kind of stability, as though the core were quietly keeping time inside the cloud left by the explosion. That rotation is not perfectly unchanging. As the neutron star emits radiation and transfers energy to particles around it, it gradually loses some of its rotational energy, causing each turn to become slightly slower over time. The change is far too small to notice in only a few observations, but when many pulses are measured across months and years, the interval between them begins to increase. This allows astronomers to estimate how the pulsar is aging and how much energy it has lost since it formed. A pulsar therefore does more than reveal the presence of a neutron star within the remnant. It also preserves part of the history of the collapse. Its rotation rate, the pace at which it slows, and its position within the surrounding gas all help astronomers infer what happened when the original star came to an end. If the explosion was not perfectly balanced, the core may have received a kick that sent it away from the center, continuing through the expanding debris. Hundreds or thousands of years later, the neutron star may lie far from its original position, carrying its magnetic field and streams of high-energy particles like a lighthouse drifting through the very mist created by the explosion. As it moves through the remnant, the neutron star may sometimes leave an elongated glowing region behind it. Particles accelerated around the star interact with the gas and magnetic fields in the surrounding environment, creating a structure resembling the trail of a small object moving through a much larger expanse. From far away, that trail may allow astronomers to trace the pulsar's motion backward toward the site of the explosion, connecting its present location to a star that vanished long ago. But the influence of a neutron star is not limited to the beams it sends into space. Its rotation can continue supplying energy to the surrounding material, keeping the central region of the remnant active long after the outer shell has begun to cool. Particles accelerated by the magnetic field stream outward and interact with gas and magnetic fields within the cloud, forming a glowing region far larger than the central object itself. In this way, a stellar core only about as wide as a city can influence a structure extending across many light years. The Crab Nebula is one of the clearest examples of this process. At its center lies a pulsar, formed by the explosion that people on Earth observed in the year 1054. The original star disappeared long ago, but its remaining core is still spinning rapidly and continually supplying energy to the surrounding environment. The filaments of the remnant do not shine only because of heat left behind by the explosion. They are also surrounded by a region of high-energy particles sustained by the pulsar at the center. There is a striking contrast within that image. The central object is far too small to be seen as a luminous disk, yet the energy from its rotation spreads across an immense region, keeping the interior of the nebula glowing. The explosion ended nearly 1,000 years ago, but the motion of the core has not stopped, and every rotation continues to transfer a portion of its energy into the cloud. Within the graveyard of a star, the smallest remaining part becomes the one that keeps the longest rhythm. This source of light is different from the X-rays produced when matter falls toward a neutron star or black hole. In an accreting system, outside gas moves deeper into the gravitational field, heats up, and emits light along the way. A rotation-powered pulsar does not need a continuous supply of new matter, because it uses its remaining rotational energy to sustain its magnetic field, radiation beams, and particle streams. The two mechanisms may exist under different circumstances, but they leave different rhythms in the light. Accretion often varies with the uneven flow of gas, while a pulsar can produce repeating signals with far greater precision. Not every neutron star appears as a lighthouse from Earth. Its radiation beams may sweep in directions that never cross our position, even while the object continues spinning and sending energy into other regions of space. Some neutron stars may also have slowed down or become too faint to detect across great distances. The absence of a pulsar signal, therefore, does not prove that a remnant contains no neutron star. Sometimes the silence is simply a consequence of our viewing angle. A lighthouse may still be turning far offshore, but if its beam never points toward the coast, no one standing on land will ever see it. The same is true in the universe. What human beings detect is only a portion of what exists. Many neutron stars may still be moving quietly through their remnants, gradually cooling and spinning more slowly without sending a signal clear enough to reach Earth. When a pulsar is found, its position and rhythm help connect the compact core to the surrounding cloud. Its trail of motion may lead back toward the site of the explosion. The age inferred from its rotation can be compared with the age of the remnant, while the energy it releases may explain why the central region remains bright even after the outer shell has begun to thin. Each small clue becomes part of a larger story. A massive star once existed there. Its core collapsed. The explosion drove the outer layers away, and what remained continued spinning within the cloud. Over long periods, the pulsar's rotation gradually slows. The energy flowing outward weakens, its radiation beams grow fainter, and the glowing region around the neutron star slowly begins to fade. The lighthouse does not go dark all at once, but neither can it maintain the same intensity forever. Eventually, the pulsar may become difficult to detect, leaving behind a darker neutron star drifting through the galaxy. Even so, For thousands or millions of years before that happens, it remains clear evidence that a supernova remnant is not completely still. Within the slowly dispersing gas lies a tiny object that continues to rotate, send energy outward, and mark the passage of time with regular pulses of light. Nuclear fusion has ended, but the star's deepest motion continues in another form. Not every core stops collapsing at the neutron star stage. Some stars leave behind cores too massive for any pressure to halt the collapse, causing the matter to continue falling inward until a black hole forms. There is no luminous surface there and no steadily turning lighthouse to reveal its position. The core becomes dark and can be recognized only through its influence on matter, light, and motion in the surrounding region. Beyond the clear rhythm of a pulsar lies a deeper kind of silence. At the center of some stellar remnants, no regular signal emerges, yet gravity remains quietly present, drawing gas into new orbits and revealing the darkness of a black hole through the very light it causes to appear nearby. Beyond the steady pulses of a pulsar lies a deeper kind of silence. In some collapses, the core does not stop at the neutron star stage, but continues contracting until no force remains strong enough to prevent the matter from falling inward. A black hole forms where the center of the star once existed, but it carries no luminous surface and sends no sweeping beam of radiation through space. Within the expanding layers of hot gas, the new core may almost completely disappear from view, even though its gravitational field continues to influence everything nearby. This disappearance does not mean the black hole is no longer present. It still retains part of the mass of the former star and remains within the region shaped by the explosion, but it sends no light of its own directly toward an observer. Without matter falling into it, a black hole may exist in an extremely quiet state, hidden among glowing ribbons of gas and the galaxy's many other X-ray sources. The region with the strongest gravity may sometimes be the most difficult part to see. For this reason, we usually do not find black holes by looking directly at them, but by observing what moves around them. If a companion star remains, its orbit may reveal an invisible mass pulling it along. The star's light shifts very slightly with every revolution, showing that it is not alone even though its companion appears in no ordinary image. In cases like these, absence itself becomes part of the evidence. Something massive enough to control the orbit is present, yet it does not emit light like a normal star. When that hidden mass exceeds the limit a neutron star can support, a black hole becomes the most reasonable explanation. We do not see the object itself, but we see that the surrounding space could not move as it does without the object being there. If gas from a companion star or from the remnant itself enters this gravitational region, the darkness begins to acquire a border of light. The material is drawn along curved paths, spirals faster, and grows hotter before reaching the deepest region. The black hole remains dark, but the surrounding flow of gas may emit powerful X-rays, like an invisible hollow revealed only by the way the current bends toward its center. Within a supernova remnant, this signature is not always easy to interpret. Gas heated by shock waves also produces X-rays. Denser regions of matter may glow more brightly, and an accreting neutron star can create a similar source of energy. A point of light within the cloud cannot reveal on its own whether the hidden object is a black hole or a neutron star. The answer lies in how the source changes, where it is located within the remnant, and what motions can be measured around the central region. If the flow of matter toward the black hole is weak, the X-ray source may also be so faint that it almost blends into the background. Most of the star's outer layers have already been thrown far away, while the amount of gas falling back gradually declines over time. The black hole has not ceased to exist. It simply lacks enough surrounding matter to reveal its presence. Its gravitational field remains, but there is not enough hot gas to transform that invisible influence into light. This is what makes searching for black holes within remnants more difficult than finding pulsars. A pulsar may send regular pulses far into space, while a black hole produces no rhythm of its own. If it has no companion star and no glowing gas around it, there may be almost no clear sign marking its location. A massive core may lie within an enormous cloud and leave behind little more than silence. The explosion does not necessarily leave the core at the geometric center of the remnant. If the collapse was not perfectly symmetrical, the black hole may receive a new velocity and continue traveling through the expanding gas. After many years, it may lie far from where astronomers expect it to be, making a search focused only on the center incomplete. But unlike a pulsing neutron star, a moving black hole leaves no regular signal that can easily be followed. The black holes we detect are therefore usually the ones whose surroundings make them visible. A companion star creates a measurable orbit. A stream of gas produces X-rays. A region of hot matter reveals that a powerful gravitational field is active beneath it. Quieter black holes may remain scattered throughout the galaxy, giving off no light and producing no motion obvious enough to be recognized from afar. Within a stellar graveyard, darkness is not necessarily an empty space. It can be a region of influence with no visible surface, where any matter passing nearby must alter its path. If a pulsar resembles a lighthouse actively sending pulses into space, a black hole is more like a deep vortex revealed only by the way gas, dust, and light bend toward it. The difficulty becomes even greater when the core is covered by material from the explosion itself. Dust may absorb visible light, hot gas may cause X-ray sources to overlap, and layers of matter moving at different speeds create a complex central region. One telescope may detect warm dust, while another sees heated gas, yet the object hidden inside may still remain concealed. Each wavelength opens only one layer of the scene, while the final answer may still lie behind all of them. There is something paradoxical about the way we search for black holes. To recognize the darkest objects, astronomers must look more carefully at the light around them. A star moving in an unusual way, a region of gas heating for no obvious reason, or a changing X-ray source may become a clue. A black hole does not tell its own story directly, but nearby matter is always compelled to respond to its presence. Even then, these responses are not always enough to support a definite conclusion. The same region of hot gas might be explained by a neutron star, a black hole, or a shock wave passing through dense material. Science must therefore allow several possibilities to remain open until the data begin to favor one clearly. The mystery does not exist because we lack an appealing hypothesis, but because the available light is not yet sufficient to distinguish among the possibilities. One of the places where this limit is most clearly revealed is the remnant of SN 1987A. When the light from the explosion reached Earth in 1987, astronomers were given the opportunity to observe a nearby supernova with modern instruments. Since then, the surrounding gas and dust have been studied across many wavelengths, and individual rings of material have been seen brightening as shock waves pass through them. Yet the stellar core has still not revealed itself in a completely unambiguous way. Within that central region, there are signs that a source of energy remains hidden behind the dust, but its nature must be interpreted with great care. It may be a young neutron star still concealed from view. The core may also have followed a different path, although current observations do not allow a simple conclusion. The very material created by the explosion has become both the evidence and the veil covering the answer. SN 1987A is therefore like a stellar graveyard being observed almost year by year, where the outer shell grows increasingly clear while the heart within preserves its deepest secret. Light from hot gas, warm dust, and shock waves has revealed a great deal about the explosion, yet the central object has not emerged as a clearly visible lighthouse or as an accreting source bright enough to be identified immediately. Within one of the most closely monitored remnants, the most difficult thing to see is still what lies at its very center. To move closer to the answer, we must look through warming dust, regions of gas changing in brightness, and subtle signs that a source of energy remains buried deep inside. There, SN 987 preserves not only the traces of a star that has died, but also the hidden identity of the core that continues to exist after the explosion. At the center of SN 1987A, the answer has been there for nearly 4 decades, yet it has never appeared as a clear point of light. The layers of gas thrown outward by the explosion are still expanding, and the outer rings of matter have brightened, one after another, as the shock wave passes through them. Meanwhile, the core of the former star remains hidden behind a thick veil of dust. The more closely we observe, the more clearly the structure of the remnant comes into view. Yet for a very long time, its most important object has also remained the most difficult to see. The light from the explosion reached Earth in February 1987, coming from a star in the Large Magellanic Cloud, a small galaxy near the Milky Way. Before the new star appeared in the sky, detectors on Earth recorded a brief burst of neutrinos lasting only a few seconds. These particles, which interact only very weakly with matter, escaped from deep within the core and arrived about 2 hours before the visible light, carrying evidence that an extremely powerful collapse had just taken place inside the star. From the beginning, astronomers knew that the explosion must have left behind a compact object. The core might have become a neutron star, or if the collapse continued, it could have formed a black hole. But there is a vast distance between knowing that an object must exist and actually detecting evidence of it. SN 1987A was still extremely young, and its interior remained filled with dense material and newly formed dust, making the central region feel like a room whose door had just closed after the explosion. The most familiar image of SN 1987A is a nearly circular ring of light surrounding the center. That ring was not created by the explosion itself. It had already formed while the star was still alive and continuously releasing gas into the surrounding environment. After the supernova, the expanding shock wave eventually reached the ring, compressing and heating the gas along its path. Bright spots appeared one by one around the rim, making it resemble a strand of beads gradually being illuminated in space. This spectacle allowed us to follow the explosion as it moved into the surrounding environment almost year by year. The bright spots intensified, spread, and changed as the shock wave continued through the ring. But the brilliance of the ring also drew attention away from the central region, where younger layers of material still concealed the core. The outside became increasingly easy to observe, while the interior continued to preserve a deeper darkness. The gas near the center is neither flat nor uniform. It contains clumps of matter ejected at different speeds, interspersed with regions of cooler dust that formed as the gas began to lose heat. Dust absorbs much of the visible light and releases that energy again at infrared wavelengths, allowing the hidden object to remain concealed, even if it is still producing energy. Like a lamp placed behind several layers of curtains, its direct light may never reach the observer. Yet, heat and changes in the surrounding material can still reveal that the space behind them is not completely dark. For many years, telescopes searched for signals commonly associated with a young neutron star. Astronomers looked for steady radio pulses, a distinct X-ray point, or a region of high-energy particles resembling a small nebula around a pulsar. But SN 1987A did not provide its answer so simply. No obvious lighthouse beam swept across Earth, and no central source appeared clearly enough to be separated from the overlapping hot gas and dust. This prolonged silence kept the possibility of a black hole open, but it did not rule out a neutron star. A young neutron star could remain completely hidden by dense material. Its radiation beam might not be directed toward Earth, or its magnetic field and rotation rate might not produce an easily recognizable pulsar. In a remnant this young, failing to see the object does not mean it is absent. Sometimes, the light has simply not yet found a path through everything the explosion left behind. The situation began to change when the James Webb Space Telescope observed SN 1987A in infrared light. Infrared wavelengths pass through dust more easily than visible light and allow regions of matter to be distinguished by their temperature and chemical composition. Instead of searching for a star-like point of light, astronomers examine subtle spectral lines in the gas near the center, because atoms can preserve the influence of an energy source that remains invisible to us directly. Within those data, argon appeared in highly ionized states close to the original site of the explosion. An atom becomes ionized when it loses one or more electrons, and removing several electrons in succession requires radiation with enough energy to do so. The gas could not naturally remain in such a state merely because it retained a little heat from an explosion that occurred decades earlier. Some source near the center must still be supplying energy to it. This clue is more subtle than a direct image of a neutron star. Yet it is very difficult to explain without a young object emitting high-energy radiation. The models that best fit the evidence point toward a newly formed neutron star. It may still be extremely hot and gradually cooling, with radiation from its surface ionizing the nearby gas. Or it may have already begun creating a small pulsar wind nebula, where high-energy particles flow outward and transfer energy to the surrounding matter. These two possibilities are not identical. In the first, we are seeing the influence of heat from a very young neutron star. In the second, its rotation and magnetic field have already begun organizing particle flows into a more active environment. But whichever path is correct, both place a neutron star at the center of the remnant and make a black hole less consistent with the newly observed evidence. What is especially remarkable is that the object itself has still not been seen as a separate form. We do not have a clear image of its surface, nor have we detected a regular sequence of pulses that would allow its rotation rate to be measured directly. What we see is its influence on nearby argon and sulfur atoms. An object only about as wide as a city has left its signature in the way electrons are removed from atoms, and from that subtle change, astronomers have traced the energy source hidden behind the dust. This method of discovery is perfectly suited to the nature of stellar graveyards. The core does not always emerge from the darkness on its own. Sometimes the surrounding environment becomes the storyteller. Ionized gas, warmed dust, and unusual particle flows carry information outward, like gentle ripples on a surface, revealing that something beneath it is still moving. SN 1987A also shows that science rarely moves forward through a single decisive moment. The neutrino burst in 1987 revealed that the core had collapsed. Later, infrared observations showed that dust was concealing a warm source at the center. X-ray and radio data added further constraints, and Webb's spectrum eventually revealed gas that could exist only in the presence of a high-energy radiation source. No single step closed the entire story, but when placed together, they gradually made the veil thinner. The neutron star may lie slightly away from the exact geometric center of the bright ring, because the explosion did not necessarily eject matter with perfect symmetry. It may also be moving behind the densest clumps of dust, causing light from the region around it to follow different paths before escaping. Future observations will seek not only to confirm that the object exists, but also to understand how it is cooling, whether it is rotating rapidly, and whether a very young pulsar wind nebula has already begun to form around it. If this becomes more clearly confirmed, SN 1987A will offer a rare opportunity. The Crab Nebula shows how a pulsar can continue supplying energy to a remnant nearly 1,000 years after the explosion. But SN 1987A allows us to look into the earliest decades, while the neutron star is still wrapped in material from the explosion itself. This is a stage that most other remnants passed through long before human beings had telescopes powerful enough to observe it. Between the glowing ring and the layers of dust near the center, two rhythms of evolution are unfolding at once. The shock wave is moving outward, striking material the star released before it died. Farther inside, the tiny core is cooling, perhaps beginning to produce a wind of particles and slowly revealing its presence. One process is expanding into the galaxy, while the other remains concealed within the central region. The heart of SN 1987A, then, is no longer completely silent. It has not yet appeared as a clearly defined lighthouse, but the gas around it has begun to carry the signature of a young energy source. Ionized atoms have become faint echoes from behind the dust, suggesting that the core most likely did not continue collapsing into a black hole, but still exists as a neutron star. That answer still requires further clarification, but it has already changed the way we view the center of the remnant. What once appeared to be only a dark region is now understood as a place where an energy source is quietly influencing the surrounding matter. The dust is no longer simply hiding the answer. The way it warms, glows, and responds to radiation is helping the answer gradually emerge. In the years ahead, the ring of SN 1987A will continue to change as the shock wave moves through it and travels beyond. The gas near the center will also become more diffuse, allowing light from the core to find clearer paths outward. Perhaps one day, the neutron star's rotation will be detected directly, or the pulsar wind around it will appear as a distinct structure of its own. For now, however, the greatest meaning of SN 1987A lies not only in the identity of the object hidden inside. This remnant shows that the death of a star does not create a fixed scene. From year to year, the shell continues colliding with its surroundings. The dust changes temperature, the gas changes state, and the core gradually reveals itself through new signs. The stellar graveyard is still evolving before our eyes. As the hidden heart begins to reveal its influence, the story also expands beyond the central region. The shock wave has reached the ring the star created while it was still alive, and it will continue farther outward, encountering other layers of gas within the galaxy. From this point on, the remnant is no longer only the private history of a single star. Its motion is beginning to merge with the larger environment surrounding it. As the shock wave of SN 1987 moves beyond the layers of matter closest to the star, it does not enter a completely empty void. Ahead of it are streams of gas the star shed long ago, tiny grains of dust suspended between the stars, and regions of matter shaped by earlier generations of celestial objects. The remnant does not simply expand like a shell released freely into darkness. Every part of its journey carries it into a different environment, and each encounter further changes the shape, speed, and light of the gas spreading outward. The space between stars is extremely thin, but it is not entirely empty. Across vast volumes, atoms, molecules, dust, and magnetic fields are still present, together forming the environment in which stars are born, move, and eventually return their material. A single gas particle has almost no meaningful effect on the remnant, but as the shock wave travels across many light years, the matter accumulated along its path gradually becomes substantial enough to alter its motion. During the first years after the explosion, the ejected material still carries tremendous speed. It races through the space surrounding the star, bearing the energy of the collapse and elements that once lay deep within the core. But as the remnant travels farther, it sweeps more and more galactic gas into its motion. The outer shell gradually ceases to consist only of matter from the former star and becomes a mixture of material thrown outward by the explosion and material that was already present in the surrounding environment. At the outer edge, the shock wave compresses and heats the gas it encounters. Matter that was once cold and diffuse is forced into faster motion, atoms are disturbed, and some of the gas begins to glow. The arcs and delicate filaments visible through telescopes mark the places where this collision is easiest to recognize. They are not fixed outlines, but constantly shifting boundaries between regions that remain undisturbed and regions that have just passed through a powerful transformation. If the surrounding environment is relatively uniform, The remnant may preserve an almost circular shape for a time, but the galaxy is rarely so even. In one direction, the shock wave may pass through extremely thin gas and continue expanding more quickly. In another, it may encounter a dense cloud, slow down, and brighten as more matter is compressed into a smaller region. Over thousands of years, a shell that was once nearly symmetrical may become elongated, distorted, or divided into uneven regions of light and shadow. The shape of a remnant therefore preserves more than the imprint of the explosion. It also becomes a map of the environment through which the shock wave has traveled. A bright section of the rim may reveal where the shell has just encountered denser gas, while a region extending farther outward may mark a direction where space is more diffuse. By studying this structure, astronomers can read both the history of the dead star and the distribution of the galaxy around it. When the remnant encounters a cold cloud, the collision does not stop at the surface. Some of the energy enters the cloud, compressing it and setting it into motion, while other flows of gas are reflected back into the hotter region behind the shock. Layers of moving matter overlap, creating curves, bright knots, and small vortices. The cloud can no longer remain in its former state, and the remnant cannot pass through without being changed in return. The magnetic fields carried within the gas are swept along as well. As matter is pressed closer together, the magnetic field lines are compressed and become stronger in certain regions. A small number of charged particles may gain additional energy as they repeatedly change direction within this environment, then escape the remnant and continue traveling through the galaxy. But most of the energy is still shared with the nearby gas, heating it, driving stronger motion, and leaving the environment different from what it was before the shock wave arrived. Although the remnant begins with violent motion, it cannot preserve its original speed forever. The more matter it gathers, the more mass must be pushed along, while the energy of the explosion is spread across an ever larger region. The shock wave gradually slows, the temperature behind it falls, and regions that once emitted powerful X-rays begin to change the way they shine. As the gas cools, electrons gradually return closer to atomic nuclei and release energy at other wavelengths. Delicate glowing filaments may become more visible in ordinary light, not because the explosion has been awakened again, but because the matter is passing through a stage of cooling and reorganization. That light is a sign that the remnant's energy is shifting away from rapid motion and extreme heat into gentler states. As the expansion slows, the boundary between the remnant and its surroundings begins to blur. Layers of gas sliding past one another form vortices, drawing material from the interior outward and carrying galactic gas deeper inside. Elements that once belonged to the old star gradually lose their separate location, blending into a broader mixture with no clear line dividing one origin from another. This process unfolds far more slowly than a human lifetime. A remnant may preserve a recognizable form for tens of thousands of years, yet the mixing begins quietly from the moment it starts sweeping up the surrounding gas. Every disturbed region carries some of the star's material out of its private history and places it within the larger motion of the galaxy. A stellar graveyard, then, is not a sealed place. Its ashes do not remain forever around the central core, but continue through new transformations. The core may endure as a neutron star or black hole, while most of the star's original mass gradually disperses, cools, and becomes part of the interstellar environment. Within that material are elements once created deep inside the star. Oxygen, carbon, silicon, iron, and many others are carried away from the core, mixed with gas already present in the galaxy, and return to the wider circulation of matter. Some become embedded in tiny grains of dust. Some remain within clouds of hot or cold gas. No atom belongs exclusively to the star that created it any longer, yet that origin remains preserved within the structure of the matter itself. In regions where many massive stars are found, the influence of their remnants may overlap and continue from one generation to the next. Stellar winds move outward first, and later explosions expand into cavities that have already been carved into the surrounding gas. An older shell may meet a younger one, keeping the environment in constant motion. A galaxy is not a motionless backdrop behind the lives of stars, but a space continually reshaped by light, winds, and explosions unfolding across many generations. This disturbance does not lead to only one outcome. In one place, a shock wave may tear a cloud apart and drive its gas away, temporarily interrupting the formation of new stars. Somewhere else, the gas may be compressed into a denser region where gravity has a better chance to draw matter together. The same explosion can break apart one structure while creating new conditions in another nearby region. What is certain is that the environment is no longer what it was before. The gas has been given additional motion, dust has been heated or destroyed, magnetic fields have been compressed, and new elements have entered the mixture. A remnant becomes one of the ways a galaxy redistributes matter and energy, carrying what once belonged to a single star into a region of space far larger than the star itself. Over time, the shell continues to slow until its motion is no longer clearly different from the flows of gas around it. The glowing filaments fade, the edges disappear, and the remnant can no longer be recognized as a separate structure. There is no precise moment marking when it vanishes. It simply blends more deeply into its surroundings, like a small stream gradually losing its shape as it enters a vast sea. Yet even after the boundary disappears, the remnant's influence remains. Its energy has set gas into motion, fast-moving particles have traveled far away, and heavy elements continue drifting through the galaxy. The remnant no longer exists as a luminous ring, but everything it contributed to the environment continues to take part in the changes that follow. In this way, the graveyard of a star gradually opens rather than closes. It does not keep its matter contained, but gives that material to clouds, streams of gas, and regions of space that have not yet taken on a clear form. The death of a single star becomes part of a much broader movement in which matter is scattered, mixed, and left to wait for new conditions. Somewhere in the galaxy, part of that gas may enter a colder cloud. Atoms that once rested inside a stellar core may attach themselves to dust, drift through the darkness, or slowly be drawn together by gravity with atoms from many other sources. This process may take millions of years, and not every fragment of matter will arrive in the same place. But from the moment the remnant blends into the galaxy, a new journey has already begun. The old star no longer exists as a luminous body, but its matter has not reached the end of its path. As the shell dissolves into the surrounding environment and its elements travel into colder regions, the stellar graveyard begins to carry the possibility of something entirely different. Within dark clouds, slowly contracting under gravity, some portion of the dead star's ashes may one day enter the light of a new generation. Within dark clouds slowly contracting under gravity, the matter of a dead star no longer carries the shape of the explosion that released it. The gas has cooled, the dust has blended into the surrounding environment, and elements that once lay deep within the stellar core now drift among countless atoms from many other sources. No boundary remains to show which fragments belong to the old star and which had already existed in the galaxy. All of it enters a slower flow of motion, where gravity gradually gathers cold regions of gas into new structures. Molecular clouds are among the places where this happens. They are cold, dark, and dense enough for atoms to combine into molecules, while dust helps shield their interiors from some of the radiation produced by surrounding stars. Invisible light, these regions often appear as dark gaps against a background of stars, but that darkness is not emptiness. It is a place where matter is gathering, where temperatures are low enough for chaotic motion to soften, and gravity has a chance to draw the denser regions closer together. A supernova remnant does not simply transform itself into a star-forming cloud. Most of its material must travel a long path, becoming diluted, mixing with galactic gas, and passing through many stages before reaching a region that is both cold and dense enough. It may take millions of years for an atom to leave an expanding shell, blend into the interstellar environment, and eventually become part of a new cloud. On such timescales, the death of one star and the birth of another are rarely connected by a short or clearly defined path. Yet the connection remains within the matter itself. Elements heavier than hydrogen and helium, created inside stars or during the violent events near the ends of their lives, do not disappear when those stars break apart. They are released into the galaxy, carried within gas, attached to dust, and drawn into later gatherings of matter. A star-forming cloud is not made from the ashes of a single star, but from a mixture left behind by many generations that lived and died before it. Within that mixture are carbon, oxygen, silicon, iron, and many other elements. They make up only a small fraction compared with hydrogen and helium, yet they play an important role in how the cloud cools, how dust forms, and how solid planets may eventually take shape. A new generation of stars is therefore not entirely like the universe's earliest generations. It is born within an environment that has been recycled many times, carrying an ever richer chemical record of the stars that came before. When one region of the cloud becomes dense enough, gravity gradually begins to overcome the motions pushing matter apart. The gas contracts, the density rises, and the center grows warmer as the energy of collapse is confined within a smaller volume. There is no single instant when a cloud suddenly becomes a star. It is a slow process in which faint, cold regions gradually develop into denser cores and then into protostars still gathering matter from their surroundings. Material that once belonged to a dead star can enter this new structure without carrying any obvious mark of its past. An oxygen atom that once rested in a deep layer of a massive star may become part of a grain of dust. That grain may drift through the cloud, be drawn into the disk around a protostar, and eventually become part of a forming planet. Over time, its origin is no longer revealed by its location, yet it remains preserved within its chemical identity. Not all matter, from a remnant, will find its way into a new star. Much of it may continue drifting through the galaxy, remain within regions of hot gas, or be carried far from places where stars are forming. Some atoms may never become part of another planet or star. The universe does not arrange every fragment of ash along a predetermined path. It creates countless possibilities, then allows gravity, temperature, and motion to determine where the material will travel. A supernova shockwave can sometimes help compress a nearby cloud. When the expanding shell reaches a cold, dense region, it may push some of the matter closer together, carrying areas already near the threshold of collapse one step further. Yet the same shockwave can also tear a cloud apart or drive its gas away, depending on the energy, distance, and structure of the environment. A supernova is therefore not simply a flame that gives birth to new stars. It is one of many influences that can alter the fate of a cloud. In one place, the explosion may interrupt star formation. Somewhere else, it may create compressed regions along the edge of a bubble of hot gas. Over millions of years, those regions may become sites where cold cores appear. But it is often difficult to say that one particular star was born because of a single explosion. A galaxy is shaped by many overlapping flows, where stellar winds, radiation, magnetic fields, and gravity all act upon the same clouds. Whatever path leads to collapse, the matter within a new star still carries the history of the environment that created it. The star's spectrum reveals the abundance of heavy elements, offering clues about how many generations of stars enriched the original cloud. The oldest stars generally contain fewer heavy elements, while stars born later formed from material that had already passed many times through stellar cores, stellar winds, and explosions. The solar system formed within an environment like this. The Sun is composed mostly of hydrogen and helium, but the rocky planets, the oceans, and living bodies require elements created in earlier stars. The carbon in organic matter, the oxygen in water, the silicon in rock, and the iron in planetary cores all carry histories far older than Earth. They existed elsewhere before, within other clouds and inside stars that are now gone. This does not mean that every atom in our bodies came from a single supernova. Elements have many different origins. Some were created in lower mass stars and later released into space. Some came from massive stars, and others were formed during rarer events. Together, however, they tell a broader story. Matter from one generation of celestial objects can continue into the generations that follow. As the protostar at the center of the cloud continues gathering matter, the remaining material around it often forms a rotating disk. Within that disk, dust grains collide, stick together, and gradually build larger structures. Planets, asteroids, and comets begin with tiny particles, including grains, carrying elements once formed deep inside ancient stars. An explosion does not directly create a planet, but it may provide some of the material the galaxy will reuse much later. Seen in this way, the birth of a planetary system is not entirely separate from the deaths that came before it. Each generation is built from matter left by many earlier generations, yet the new form does not repeat the old one. An atom once held within the core of a massive star may become part of a small planet. A dust grain that once passed through a shock wave may later rest within the ice of a comet. Matter continues to exist, but its role is always changing. This is also why a stellar graveyard is not the end of the galactic cycle. The remnant gradually loses its boundaries, yet its matter and energy continue participating in structures that form later. Some remains locked within a neutron star or black hole. Some spreads into the interstellar environment, and some enters cold clouds. There is no single path, only many branches of motion beginning from a star that has lost its original form. Time makes that connection difficult to see. An explosion lasts only a short while its material may need millions of years to enter a new cloud, and millions more to become part of a planetary system. Viewed as separate events, they seem unrelated. But when the galaxy is observed across longer spans of time, death and birth become connected within a continuous flow of reuse. Within that flow, there is no rebirth in the sense that the old star returns. The dead star will never recover its former shape or light. The atoms that once belonged to it are dispersed, mixed, and drawn into structures that no longer carry its identity. What continues is not the individual star, but its matter, its energy, and the possibility of forming something new. A dark cloud may hold matter in an almost motionless state for an immense length of time before one small region begins to contract. A protostar appears, its first light escapes through the dust, and a disk of material forms around it. No one is there to recognize that this new light contains atoms that once rested inside a star that died millions of years earlier, yet the connection remains within the composition of the system itself. When we look at a supernova remnant, then, we are not only seeing matter leaving a star, we are also watching material begin a journey with no predetermined outcome. Some of it will continue drifting, some will remain within dust, and some may enter stars and planets that have not yet formed. A stellar graveyard does not create new worlds by itself, but it returns to the galaxy materials the galaxy may use in the future. At the edge of a cold cloud, this process leaves almost no dramatic sign. Gas simply gathers slowly, dust conceals the light, and gravity works across timescales far longer than a human life. Yet within that silence, matter that has passed through fire, pressure, and explosion begins to find a new place. A dead star does not become another star, but part of it may one day exist within the light of a later generation. There is no clear doorway between an ending and a beginning, only motions extending across the galaxy, where matter continually loses its former shape and enters new structures. And as the story approaches its end, what remains is more than an image of stars that have disappeared. It offers another way of seeing the universe itself, not as a collection of separate objects that live and die in isolation, but as an ever-changing flow of matter, where every boundary between a remnant and a beginning exists only for a time. When a star reaches the end of its life, its familiar light may fade very quickly, but everything that belonged to that star does not disappear with its final moment. The core contracts into a neutron star or black hole, the outer layers expand into space. A companion star may continue living, and the old orbit may be broken apart or rewritten. From a great distance, we often see the explosion as a final period, but within the galaxy, it is only the moment when many new paths begin at once. The remnant continues to expand, colliding with interstellar gas and gradually losing its distinct shape. Elements that once lay deep within the star are carried outward and mixed with dust, gas, and matter from countless other generations. The surviving core may rotate in the darkness, send beams of radiation through space, or quietly draw material toward itself. If a companion star remains, the two continue influencing one another through gravity, motion, and delicate streams of gas too faint for human eyes to see. None of these processes resembles new life in the familiar sense, yet all of them show that the death of a star is not a motionless state. Heat continues to travel. A stellar graveyard is therefore not a place of absolute silence, but a region of transition where the old form has vanished while deeper motions continue beneath the surface. Throughout this journey, each layer of observation reveals a different face of the same remnant. Visible light shows delicate filaments of gas and expanding arcs. X-rays reveal hot gas, accreting matter, and small sources of energy hidden within the cloud. Radio waves may uncover rapidly moving particles and the rotating rhythm of a pulsar. Infrared light passes through dust, revealing regions that familiar light cannot reach. No single form of light can tell the entire story, but when they are placed together, they make a past that seemed finished feel active once again. The variable points of light in M83 show that a remnant may contain systems that are still active. A surviving star may continue supplying matter to the compact core. Gas from the explosion itself may slow down and fall back inward. A neutron star may rotate like a lighthouse within the cloud, while a black hole reveals its presence only through the light and motion around it. In SN 1987A, the core remains behind several layers of dust, yet atoms near the center have begun to carry the signature of a young energy source. All of these cases are different, but each one blurs the boundary between an object that has died and a system that is still changing. The former star no longer sustains nuclear fusion as it once did, but what remains has not come to rest. A stellar core may continue spinning. A black hole may continue pulling in matter. A companion star may carry traces of the explosion in its speed, chemical composition, and orbit. A layer of gas that seems merely to be cooling may still brighten when it encounters denser material. Over time, these signs will also fade. A pulsar spins more slowly, accretion weakens, the remnant's shell blends more deeply into its surroundings, and the elements of the former star spread across an increasingly vast region. There is no clear moment when the remnant ceases to exist. Its form simply becomes less distinct until no boundary remains sharp enough to separate the material of the explosion from the rest of the galaxy. But the disappearance of that boundary does not mean the matter itself is gone. The atoms continue drifting, attaching themselves to grains of dust, passing through clouds of hot gas, and cooling within darker regions. Some may remain in interstellar space for an immense length of time. Others may be drawn into contracting clouds, where they take part in the formation of stars, planets, and objects that have never existed before. No star is reborn directly from its own ashes along a simple path. The material becomes so thoroughly mixed that its individual origins nearly disappear, and a new stellar system is formed from the contributions of many different generations. Yet this very mixing allows the galaxy to preserve what earlier stars created. Each generation leaves some of its matter to the next, not as a copy of the past, but as the raw material for entirely new structures. The universe therefore does not build permanent walls between endings and beginnings. Those boundaries appear only when we observe an object across a short span of time. A star is born, lives, and dies, and this may seem like a complete story, but on the scale of a galaxy, it is only one stage within a much longer flow. Gas becomes a star. The star returns matter to space. That matter enters a cloud, and another structure begins to form. What continues is not the identity of the former star. It will not return with the same mass, shape, or light. What continues is its matter and energy, the elements released into the galaxy, the motion transferred into the surrounding environment, and the changes the explosion left behind in nearby space. The past is not preserved exactly as it was, but neither is it completely lost. It is dispersed, transformed, and made part of what appears later. Seen in this way, a supernova remnant is no longer only an image of destruction. It is a place where several different times coexist. The outer gas preserves the imprint of the explosion. The compact core carries the history of the star that came before. A companion star moves into the future, bearing the changes written into it. The elements within the cloud move towards structures that have not yet been born. In one place, light is fading. Somewhere else, a cold cloud is beginning to contract. The two processes may be separated by millions of years and thousands of light years, yet they still belong to the same galactic flow of matter. The universe does not need to keep them close together for the connection to remain. As long as matter continues moving, what was once the ending of one star can become a very small part of the beginning of another system. Perhaps this is the deepest meaning left by stellar graveyards. They do not deny the death of stars, nor do they turn every ending into a simple story of hope. The star has truly lost its former shape, and nothing can reverse that moment. But this loss does not make everything that once formed the star meaningless. The matter remains, the motion remains, and its influence continues traveling through time. Across the vastness of space, no sound marks the moment when a remnant fully blends into the galaxy. There is no line showing where death ends and formation begins. There is only gas slowly mixing together, dust drifting through darkness, gravity drawing regions of matter closer, and light appearing somewhere else after an immense passage of time. The dead star does not return, but the universe does not close its story. The core continues spinning or remains hidden in darkness. The ashes continue traveling through the galaxy. The elements continue finding places within other clouds, planets, and stars. Forms change and names change, but matter continues its journey. And when we look back at a remnant, slowly fading into space, we may see not only a light that has gone out, but countless motions that have not yet reached their end. A layer of gas is blending into the galaxy. A tiny object is spinning behind a veil of dust. A stream of matter is falling into a deep gravitational field, and atoms are beginning a long journey toward a place that does not yet exist. Within that silence, the universe does not hurry to distinguish between an ending and a beginning. It simply continues moving matter from one form into another across timescales greater than any individual life. And perhaps that is why the graveyards of stars have never truly been empty. The light may have faded, but the motion remains. Thank you for joining Sleep Gravity on this journey. Now, as those distant remnants continue expanding through the darkness and cold clouds quietly wait for a new generation, you can let those motions drift slowly away, calm and unhurried, as your mind gently settles into the rest of the night.